What if everything you thought you knew about the universe was wrong? From time loops to minds that shouldn't exist, these paradoxes don't just challenge science, they break it. Welcome to a world where logic collapses, reason bends, and even the brightest scientists are left speechless. These are the paradoxes that break reality, and once you hear them, you'll never see the world the same way again. Fermi Paradox. The night sky stretches vast and silent above us, littered with stars, each one a possible sun to a world like our own. For millennia, humans have gazed upward and wondered if we're alone. In a universe that seems infinite, filled with hundreds of billions of galaxies, each containing billions of stars, it feels almost arrogant to assume Earth holds the only intelligent life. And yet, here we are, seemingly alone. This haunting contradiction between high probability and zero evidence is what we call the Fermi Paradox. Named after the physicist Enrico Fermi, the paradox arose from a simple yet profound question he once posed over lunch: where is everybody? If the universe is so vast and old, and if intelligent civilizations are likely to arise, then why haven't we seen any signs of them? No radio signals, no alien spacecraft, no mysterious structures floating between the stars, just silence. Let's break it down. The Milky Way alone contains over 100 billion stars. Many of those stars are similar to our Sun, and orbiting them are planets, some rocky, some gaseous, and many nestled within their star's habitable zone. These are regions where temperatures could allow for liquid water, one of the key ingredients for life as we know it. And here's the thing. Recent data from space telescopes like Kepler suggest there could be hundreds of millions of these potentially habitable Earth-like planets in our galaxy alone. With numbers like that, it becomes reasonable to expect that even if a small fraction of those worlds gave rise to intelligent life, there should be thousands, if not millions, of advanced civilizations. Some might be only a few centuries ahead of us, others might have achieved space travel millions of years ago. With that much of a head start, they could have colonized the entire galaxy by now, and still we've heard nothing. We've seen nothing. The cosmos remains eerily quiet. The Drake equation was one of the first formal attempts to estimate the number of extraterrestrial civilizations. It considered factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the number that actually do, the ones where intelligent life evolves, those that develop detectable technology, and finally, how long such civilizations survive. But many of these numbers are guesses. Optimists fill in large values and predict thousands of alien societies. Skeptics choose conservative numbers and conclude we might truly be alone. But even if we err on the side of optimism, the question persists: why haven't we seen them? Some say maybe we're not listening correctly. Maybe we've only scratched the surface of the electromagnetic spectrum. Our search is like standing in a dark forest and shouting once and expecting someone to hear us. Radio telescopes have only been in use for a tiny fraction of human history. Perhaps the signals are out there, but we haven't tuned in to the right frequency at the right time. Civilizations might be talking in ways we don't yet understand, using neutrinos, gravity waves, or quantum entanglement instead of radio waves. Others propose that intelligent civilizations may self-destruct before they can reach out to others. Nuclear war, ecological collapse, or artificial intelligence spiraling out of control could all lead to self-inflicted extinction. If this is a universal pattern, maybe the stars are filled with the remnants of once great societies who never made it past their adolescence. The universe might be a graveyard of silent ruins, testament to the fragility of intelligence. And then there's the possibility that advanced civilizations are out there, but they're avoiding us. Perhaps we are in a kind of cosmic zoo, deliberately shielded from contact until we're deemed ready. It's called the zoo hypothesis. Imagine ants in a garden. We might study them, even protect their environment, but we don't try to communicate. Why would a civilization millions of years ahead of us see us any differently? To them, we may not yet be interesting or safe. Another theory is that space travel might not be as practical as we once believed. The distances between stars are unimaginably vast. Even the closest star system, Alpha Centauri, is over 4 light-years away. With our current technology, it would take tens of thousands of years to get there. Perhaps even advanced societies face insurmountable physical or economic challenges when it comes to colonizing the galaxy. It could be that civilizations turn inward, developing virtual realities or post-biological existences, and lose interest in the stars. Or maybe we are the first. The universe is old, almost 14 billion years, but intelligent life might be exceedingly rare, and we may be the pioneers. If true, then our role is not just to observe the silence, but to break it. We would be the ones sending out the first signals, launching the first ships, planting the first flag on alien soil. But being first comes with responsibility and risk. Then again, maybe we have been visited but just don't recognize it. Ancient alien theories, while often speculative, tap into this very notion. Some argue that UFO sightings or unexplainable phenomena are signs of contact, misinterpreted, denied, or hidden. But extraordinary claims require extraordinary evidence. So far, no encounter has passed scientific scrutiny. Still, the idea lingers. What if they are already here, but choose to remain invisible? Another possibility is even darker. Perhaps there's a great filter, an obstacle so difficult to overcome that very few, if any, civilizations survive it. The filter could be behind us. Maybe life itself is so unlikely that it rarely emerges. Or it could be ahead of us, meaning the greatest threats are yet to come. If it's ahead, it would explain the silence. The night sky, then, is not quiet because others never lived, but because they all failed to survive, and we might be next. And yet, hope remains. Each new discovery of an exoplanet, each new whisper from distant galaxies, brings us closer to understanding our place in the universe. The James Webb Space Telescope, now orbiting far beyond Earth, is scanning the atmospheres of alien worlds, searching for the telltale signs of life, oxygen, methane, or something stranger. Perhaps within our lifetime, we will receive that first signal, a deliberate pulse from an intelligence far away, echoing through the dark. The Fermi Paradox continues to haunt scientists, dreamers, and philosophers alike. It is not just a scientific question, but a deeply human one. It touches on our fears of isolation, our desire for connection, and our hope that we are part of something larger. Whether the silence of the universe is temporary or eternal, we do not yet know. But in that silence, we continue to listen, to wonder, and to read. Because perhaps, just perhaps, someone is out there, waiting for us to say hello. Bootstrap Paradox. There's a peculiar kind of magic woven into the idea of time travel. The ability to bend the straight line of time into loops, knots, and curves ignites both wonder and confusion. Among the most haunting of these temporal riddles lies the Bootstrap Paradox, a loop in time that seems to defy logic, causality, and even the very notion of origin. It's a paradox that forces us to ask one fundamental question: where did it all begin? Or, more disturbingly, what if there was no beginning at all? Imagine for a moment that time is not a one-way street. Instead, it's a circle, a closed circuit where cause and effect swap roles and chase each other endlessly. In the Bootstrap Paradox, an object or piece of information is sent back in time and becomes trapped in this circular chain of events, with no clear point of creation. It exists, yes, but it was never truly made. It's passed from one moment to another, always existing but never born, and that's where the mind begins to twist. The paradox takes its name from the expression pulling oneself up by one's bootstraps, a task as logically impossible as its temporal equivalent. A person can't lift themselves into the air by tugging on their boots, just as something cannot bring itself into being by existing in a loop. But this is exactly what the Bootstrap Paradox suggests. Something can exist without an origin simply because time allows it to. Let's ground this in an example. Picture a man in the future, a curious historian who's always been fascinated by the works of Shakespeare. One day, he gets his hands on a time machine and decides to travel back to the Elizabethan era. But before he goes, he grabs a printed copy of Hamlet. When he arrives in the past, he meets a young William Shakespeare, still struggling to find his voice as a playwright. Wanting to inspire the man, the time traveler gives him the book. Shakespeare, intrigued and astounded, reads it, memorizes it, and eventually publishes it as his own. Generations later, that same play is printed and handed down until a copy ends up in the hands of the future historian, the very one who took it back in time. And so the loop continues. Here's the problem. Who wrote Hamlet? If the play was never originally created, only copied, passed on, and regurgitated, where did it come from? It exists, yes, but it has no author. It was never invented, never born. It simply is. This is the Bootstrap Paradox in its purest form, something that exists in time yet never originated in time. It may sound like the premise of a clever science fiction tale, and indeed it often is, but it touches on deeper philosophical and physical questions. What is the nature of causality when time becomes nonlinear? Can information or matter truly exist without a source? And if so, does that violate the fundamental laws of physics or merely our understanding of them? Time loops like this appear in literature, film, and even in serious scientific discussions. Movies such as Predestination, 12 Monkeys, and Doctor Who episodes have played with this idea, toying with the eerie sensation of encountering your own past actions out of order. It creates a space where logic breaks down, not through contradiction, but through ambiguity. There's no clear beginning or end, just a loop, a snake eating its own tail. From a physics perspective, the Bootstrap Paradox dances on the edge of what might be possible. General relativity, Einstein's grand theory of space and time, allows for the possibility of closed time-like curves. These are paths in space-time that loop back on themselves, theoretically allowing for time travel to the past. In such a scenario, an object or person could follow this loop and return to a previous point in time. But when you introduce information or material into this loop, especially self-referentially, you begin to tease the edges of paradox. The paradox, however, is subtle. It doesn't create a contradiction the way the grandfather paradox does, where killing your ancestor erases your existence and thus your ability to travel back. In the Bootstrap Paradox, everything lines up neatly. The object or information doesn't create a conflict, it just lacks an origin. Everything functions smoothly, but there's no point of creation. And that's precisely what makes it so unsettling. It's a paradox of ontology, a paradox of existence itself. Some philosophers argue that the paradox isn't truly a paradox at all. They propose that causality, in this case, simply wraps around itself. The information is consistent through time and no rules are broken. It's a self-contained loop, and though counterintuitive, it doesn't contradict any fundamental principles. But this leads us to a deeper question. Does reality allow for such loops, or is there something embedded in the laws of nature that prevents them? Quantum mechanics, that strange and beautiful framework of the subatomic world, offers no easy answers. On one hand, quantum theory is probabilistic, chaotic, and deeply indeterminate. On the other, it holds within it the seeds of reversibility. Some interpretations even suggest that particles can affect their own past. In such a landscape, perhaps the Bootstrap Paradox is not as impossible as it seems. Maybe, under the right circumstances, information can indeed fold into itself and persist in a causeless loop. But if we accept that possibility, another problem arises. Could the universe be filled with such causeless phenomena? Could ideas, technologies, or even people exist purely because of these loops? Imagine a world where every great invention, every scientific discovery, every revolutionary thought came not from inspiration, but from a time loop. Imagine a world where Beethoven's music, Newton's laws, or even the very idea of time travel itself has no true origin. Would it matter? Would it make them any less meaningful? This is the deeper, more existential layer of the Bootstrap Paradox. It's not just a temporal puzzle, it's a mirror held up to our understanding of creativity, identity, and purpose. If we derive our knowledge from a loop, do we still own it? If a book is passed backward in time and never written, is it still literature? Or is it merely a ghost, an echo of an event that never happened? Some speculate that these loops may be rare, isolated curiosities. Others suggest they may be artifacts of a larger, deeper reality, one where time, as we experience it, is merely an illusion. In this view, the past and future coexist, and causality is not a line but a network. In such a universe, the Bootstrap Paradox isn't strange, it's inevitable. The term has also seeped into metaphysical and spiritual discussions. The idea that the universe itself might be caught in a loop, a cosmic bootstrap, where the cause and the effect are the same, where creation and creator are reflections of each other. It's a theme echoed in ancient myths and modern science alike. Ouroboros, the cosmic egg, the loop of samsara, they all point to this eternal return, this mysterious recurrence without beginning or end. Ultimately, the Bootstrap Paradox leaves us with more questions than answers. It doesn't offer closure, it doesn't resolve neatly, but that's part of its beauty. It's a riddle that doesn't require solving to be meaningful. It's a crack in the wall of reality that lets in a strange light. A light that makes us think, wonder, and question the very nature of time, origin, and existence. We may never experience time travel. We may never loop through the centuries or meet our younger selves. But the Bootstrap Paradox reminds us that time is not as simple as it seems. And in that complexity lies a strange, humbling wisdom. Not everything must have a beginning. Not everything has to come from somewhere. Some things just are. Not because they were made, but because time, unfolded just right, makes room for them. So the next time you read a book, hear a melody, or stumble upon a brilliant idea, pause for a moment. Ask yourself where it really came from. Trace it back, and then further, and further still. And if the trail disappears into a loop, an endless, beautiful circle, don't be afraid. You may have just encountered the Bootstrap Paradox in real life. Grandfather Paradox. Time travel has always occupied a curious space between science and fiction, between dreams and dilemmas. It promises to unlock the secrets of the past and offer a glimpse into the future. But what makes time travel so endlessly fascinating is not just where it might take us, but the paradoxes it might create. And among these temporal puzzles, none is more iconic or more perplexing than the Grandfather Paradox. It's a simple idea, yet one that dismantles our understanding of cause and effect, threatening to unravel the very fabric of reality. Imagine this. You build a time machine. With curiosity and a bold heart, you decide to go back in time, not to witness history unfold, but to change it. You set your coordinates for a date decades before your birth. You find your grandfather, a young man unaware of the future he's about to shape, and for reasons personal, philosophical, or experimental, you stop him from ever meeting your grandmother. Maybe you even go further, erasing him entirely, and then you return to your own time. But when you do, something is wrong. Something fundamental has changed. You no longer exist. It's a haunting thought. If your grandfather was removed from history, then your parent would never have been born. And if your parent never existed, neither would you. But if you were never born, how could you have traveled back in time to eliminate your grandfather in the first place? You couldn't have. But then he would still be alive, and you would be born, which means you could go back. And the cycle begins again. The paradox loops in on itself, creating a contradiction that cannot be resolved. This is the essence of the Grandfather Paradox, a temporal contradiction where altering the past erases the conditions that made the alteration possible. It exposes a fatal flaw in the concept of backwards time travel, at least as we currently understand it. It's not just a problem of logic, but a crisis of causality. The cause and the effect nullify one another. The future changes the past, which then erases the future that caused the change. On the surface, it might seem like a problem reserved for science fiction, and indeed countless stories, films, and books have explored its terrifying implications. From Back to the Future to Looper, from Dark to the Terminator, storytellers have returned to the grandfather paradox again and again. In each version, the consequences of meddling with the past spiral into unforeseen and often catastrophic results. Because even a small action, one misstep, can echo across generations. But the paradox is more than a narrative device. It's a serious philosophical and scientific concern. In physics, time is often treated as a dimension, like space. Just as you can move left or right, up or down, forward or backward in space, some theories suggest you might move backward in time. General relativity, Einstein's powerful theory of space-time, allows for the theoretical existence of closed, time-like curves, paths through the fabric of space and time that could loop back on themselves. In such a universe, time travel to the past might be possible, and with it, all the paradoxes it invites. The grandfather paradox doesn't break the laws of physics, but it bends them until they scream. It forces us to question whether time can truly be manipulated in reverse, or whether nature itself has built-in mechanisms to prevent such chaos. Some physicists suggest that the universe protects its own consistency. This idea, known as the Novikov self-consistency principle, argues that any actions taken by a time traveler were always part of history. In other words, you might travel back in time and meet your grandfather, but you would never be able to change events in a way that would create a contradiction. If you tried to kill him, something would stop you. The gun would jam, you'd have a change of heart, he'd survive. Whatever happens, history remains intact. This principle offers a kind of comfort, a cosmic safety net that ensures the timeline doesn't tear. But it also raises unsettling questions. Does this mean free will is an illusion? That no matter what you do, the past is locked in place, unchangeable and eternal? And if so, is the future just as fixed? Are we all trapped in a deterministic loop, playing out roles that were written long before we were born? Other interpretations of physics propose more radical solutions. The many worlds interpretation of quantum mechanics, for instance, suggests that every possible outcome of an event creates a new, branching universe. In this view, traveling back in time and killing your grandfather wouldn't erase you, it would simply create a new reality in which you were never born. Your original timeline would continue unchanged, while the new one diverges into its own path. No paradox, no contradiction, just an infinite multiverse of possibilities. But if time travel merely spawns alternate realities, it loses its emotional and narrative punch. You're not really changing your past, you're just moving sideways into a different one. And while this may solve the paradox on paper, it leaves us with a more abstract, less satisfying view of what time travel really means. There's another way to think about the grandfather paradox, not as a problem to solve, but as a mirror to hold up against our assumptions about time. We think of time as a straight line, from past to present to future. But what if that line can bend, loop, or even fold in on itself? What if cause and effect are not always linear? What if the universe is not a book read from beginning to end, but a tapestry where threads cross and twist in intricate, unknowable ways? In such a reality, the paradox becomes a signpost, not a roadblock. It points us toward the edges of our understanding, reminding us that time is not as simple as it seems. It hints at a deeper order, one we have yet to grasp. And in doing so, it humbles us. Philosophically, the grandfather paradox is a meditation on identity, memory, and consequence. Who are you, if not the result of every moment that came before? And what happens when you untangle that thread? If you erase your own lineage, do you vanish entirely? Or do you become something else? An anomaly, a ghost in the machine of time? These aren't just abstract musings. They strike at the heart of what it means to exist, to matter, to leave a mark on the world. Psychologically, the paradox stirs unease. It asks us to imagine a reality where nothing is stable, where the ground beneath our feet can be rewritten with a flick of temporal interference. It challenges the permanence of memory, the reliability of history, the logic of the world we think we understand. And yet, within that discomfort, there is wonder. The grandfather paradox reminds us of the mystery that surrounds us, even in the scientific age. That time, for all our clocks and calendars, remains one of the great unknowns. Perhaps that's why the paradox continues to endure, not because it offers answers, but because it asks the right questions. What is time? Can it be bent, changed, or defied? And if so, at what cost? What happens when you tamper with the past, and in doing so, destroy the future, or yourself? In the end, the grandfather paradox is not just a story about a man and his ancestor. It's a story about us, all of us, grappling with the limits of our power, the shape of our stories, and the boundaries of what we can change. Whether time travel ever becomes real, the paradox will remain, as a caution, as a curiosity, as a challenge to everything we think we know about time, cause, and the fragile thread of existence. So if ever you find yourself dreaming of going back, whether to relive a moment, correct a mistake, or change the course of history, pause for a moment. Consider the paradox. Consider what might be lost, not just gained. And remember that the past, for all its pain and beauty, is a foundation, not a playground. Some doors once opened may never close again, and some threads once pulled unravel everything. Taking out Hitler paradox. Time travel has a way of tempting us with the idea of moral correction. It offers a seductive thought experiment. What if you could go back and undo the darkest chapters of human history? Few figures represent such overwhelming darkness as Adolf Hitler, whose rise to power led to the devastation of World War II and the horrors of the Holocaust. So naturally, one of the most frequently discussed time travel fantasies involves going back in time and eliminating Hitler before he ever rises to power. It seems like a noble mission, almost a universal good, but buried beneath this seemingly righteous act lies one of the most troubling thought experiments in temporal logic: the paradox of taking out Hitler. On its surface, the logic is clear. Prevent the birth of a tyrant, and you prevent the atrocities he orchestrates. You stop millions of deaths, the ravages of war, the construction of death camps, and the psychological scars that would ripple through generations. With a single action in the past, the course of history could be altered for the better. But time, as we've come to understand, rarely offers such simple exchanges. What unfolds instead is a cascade of questions. If Hitler is removed, what then becomes of the timeline that produced you, the time traveler? Would you even exist? Would the invention of time travel itself still occur? And if none of it happens, who goes back to take him out? This is where the paradox begins to take shape. Imagine a world where a time traveler succeeds in preventing Hitler's rise, perhaps through intervention in his youth, perhaps through a political sabotage, or perhaps through direct elimination. As a result, the horrors of World War II never unfold. Millions of lives are spared. But with no world war, the future unfolds differently. Nations do not develop as they once did. The political, technological, and social pathways shift. Perhaps the time traveler is never born. Or perhaps, in this new timeline, time travel is never discovered, because the scientific advancements born from war, like rocketry, computing, and atomic research, are delayed or never prioritized. In this altered world, there is no motivation, no opportunity, and no method for someone to build a time machine. And if no one builds it, then no one travels back. And if no one travels back, Hitler lives, and the war happens as it originally did. Which means someone does go back. The loop is complete, but it cannot hold itself. That's the paradox. The taking out Hitler paradox is a cousin of the grandfather paradox, But it adds another layer. Not only do you erase yourself by changing the past, but you also erase the very reason for wanting to change the past in the first place. If Hitler is removed before his actions scar the world, then the motivation to remove him disappears too. The war never happens, and therefore no one has a reason to go back to stop it. But if no one stops it, it happens. And so, time collapses in on itself, not in contradiction, but in causeless repetition. There's another complication to this paradox: the unpredictability of the consequences. History is not a linear thread, it is a complex tapestry where every thread touches countless others. By removing one person, even one as influential as Hitler, you do not simply delete a page from the story of time, you rewrite the entire narrative. The rise of fascism may have found another figurehead. A war may have still broken out, perhaps earlier or later, or in a different form, and the horror that once wore a swastika might have returned under a different symbol, in a different country, with a different name. The human capacity for destruction, unfortunately, does not vanish with the removal of one man. In this light, the paradox takes on a deeper, more unsettling character. It challenges our belief that evil can be surgically removed. It confronts us with the possibility that the events we most wish to undo are not simply the result of individuals, but of systems, ideologies, and failures woven into the structure of society itself. Hitler, monstrous though he was, did not rise in isolation. He rose on the waves of economic despair, political manipulation, nationalist fervor, and a broken post-war Europe. Erasing him might not erase those currents, it might simply redirect them. Some speculate that taking out Hitler might make things worse. Perhaps his removal allows someone even more cunning or ruthless to rise in his place, someone who avoids the military blunders that led to Germany's defeat. A world without Hitler might not be a world without war, but one in which war takes a darker, more enduring shape. The Holocaust might be avoided, but new horrors might arise in its place. Without World War II, perhaps the Cold War never emerges in its known form, and perhaps the checks and balances of nuclear deterrence never take hold. The butterfly effect spreads, unpredictable and irreversible. Others invoke the many worlds interpretation of quantum theory. In this view, any attempt to kill Hitler doesn't undo your own timeline, it simply creates a new one. When you travel back and alter history, the original timeline remains intact, and you branch off into a new reality where events unfold differently. In this case, you don't solve anything, you just exile yourself into a different version of reality. Your home timeline continues on its grim path, while you watch a new history blossom. This removes the paradox, but at a cost. It suggests that time travel doesn't heal history, it only splits it. Then there's the ethical layer of the paradox. Suppose you have the opportunity to eliminate a young Adolf Hitler, a struggling artist in Vienna, poor and isolated, unaware of the path that lies ahead. Do you kill him? Is it ethical to take the life of someone who has not yet committed any crimes? Or does the weight of future suffering justify such a preemptive act? The paradox invites you to play judge, jury, and executioner, not just of a man, but of time itself. It asks, can we punish someone for crimes they have not yet committed? And if so, are we any different from the totalitarian impulses we claim to resist? Even in speculative fiction, this paradox rarely finds a satisfying resolution. Stories that entertain the possibility of removing Hitler often end with unintended consequences, dystopias more brutal than the one they tried to erase. These tales aren't just warnings against tampering with time, they're reflections of a deeper truth. History, for all its pain, shapes us. It teaches, scars, and informs the future. To erase it is to gamble with our identity. In some interpretations, the universe simply doesn't allow these contradictions to play out. Known as the chronology protection conjecture, this theory, proposed by Stephen Hawking, suggests that nature prevents time paradoxes from forming. Something, quantum noise, unstable energy, or a hidden law of physics intervenes to stop time travel from changing the past in ways that cause inconsistency. Maybe your time machine fails. Maybe you're redirected. Maybe the past resists. Reality defends itself against paradox. But even if this is true, even if time can never be changed, the thought experiment still holds power. It reveals how fragile history is and how intertwined our identities are with events we never experienced. It makes us ask, who are we in a world where the worst never happened? Would our capacity for compassion, resilience, and innovation be as strong without the crucible of suffering that shaped it? The taking out Hitler paradox is not just about time, it's about memory, morality, and the weight of consequences. It reminds us that the past is not just a collection of events, but a living context for everything we are. And while the desire to undo suffering is deeply human, the path to a better future may not lie in erasing the past, but in understanding it, learning from it, and building something new from its ashes. So as we dream of time machines and the power to rewrite history, let us not forget that the present too is a place of influence. It is here, not in the past, that our decisions unfold. It is here that we can prevent future horrors, not with a bullet in the past, but with empathy, education, and vigilance in the now. The paradox, then, is not just a puzzle for physicists and philosophers, it is a mirror for us all. Polchinski's Paradox. In the ever-deepening mystery of time, few thought experiments bend the mind quite like Polchinski's paradox. At first glance, it might seem like a physicist's riddle, something abstract, tangled in math and theory. But look closer, and you find something far more profound. A doorway into the very contradictions at the heart of time travel. Conceived by the late theoretical physicist Joseph Polchinski, this paradox challenges the nature of cause and effect by taking something incredibly simple, a billiard ball, and placing it in an impossibly complicated situation, one where it collides with itself through time. Imagine for a moment a wormhole, not just a science fiction fantasy, but a hypothetical shortcut through the fabric of space and time. General relativity allows for such structures under extreme conditions, where space-time can bend so drastically that it folds in on itself. If constructed just right, a wormhole could connect two distant regions of space, or even two different moments in time. The entrance might be today, and the exit might be yesterday. Travel through the wormhole and you've effectively traveled to the past. This is where the paradox begins. Now picture a billiard ball. It's simple, solid, and utterly non-controversial until you send it through a wormhole. In Polchinski's setup, a billiard ball is shot toward the mouth of a wormhole with just the right trajectory to travel back in time and exit the other side a few moments earlier. As it emerges in the past, it encounters its younger self on the way in. And here's the twist. It strikes its earlier version in such a way that it knocks it off course. The younger billiard ball, now deflected, never enters the wormhole. But if it doesn't go in, then it can't come out and interfere with itself. And if it doesn't interfere, it should follow the original path and enter the wormhole. And once again, the loop begins. This is the essence of Polchinski's paradox, a causal loop where an event in the future prevents its own cause from occurring. It's not just logically troubling, it's physically impossible within a classical framework. Cause and effect are supposed to be a one-way street. The past influences the future, not the other way around. But in this scenario, the future actively disrupts the past. It's a snake devouring its own tail, not gradually, but all at once. What makes this paradox especially fascinating is its elegance. Unlike more abstract or fantastical time travel paradoxes, Polchinski's is grounded in the laws of physics as we understand them. There's no need for human choices or emotional stakes. No murder of a grandfather, no rewriting of world history, just a ball, a trajectory, and a wormhole. It's clean, mechanical, and uncomfortably logical. And yet it breaks down everything we believe about how time should behave. Naturally, physicists have not ignored this challenge. Some argued that the paradox disproves the possibility of time travel altogether. If backward time travel leads to contradictions, then nature must prevent it from happening. This viewpoint aligns with Stephen Hawking's chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel on macroscopic. According to this view, wormholes that connect different times either collapse, destabilize, or become inaccessible before paradoxes like Polchinski's can unfold. But others took a different path. Instead of denying the paradox, they sought a way to resolve it, and remarkably, they found one. A group of physics students analyzed the scenario and discovered that certain self-consistent solutions do exist. In one such resolution, the billiard ball emerges from the wormhole at a slightly different angle, not enough to completely knock its younger self off course, but just enough to deflect it slightly. This deflection sends the ball into the wormhole on a new trajectory, which causes it to exit at just the right angle to deliver that very deflection. The loop closes. No contradiction, no paradox, just an elegant, self-correcting curve in time. These solutions follow a principle called the Novikov self-consistency conjecture, which states that any event occurring on a closed time-like curve must be consistent with itself. In other words, time can loop, but only in ways that preserve internal consistency. Nothing happens that would change the past in a way that creates a contradiction. The billiard ball doesn't stop itself from entering the wormhole, it merely nudges its own past into the path that made the nudge possible. This idea doesn't just resolve the paradox, it redefines our understanding of cause and effect. In a timeline governed by self-consistency, the future and the past are locked together in an eternal handshake. One shapes the other, not in sequence, but in unity. Time becomes a loop of mutual influence, where every cause is also an effect, and every effect is also a cause. It's a kind of cosmic choreography, impossible to lead or follow, because both are happening at once. Philosophically, this notion is deeply unsettling. We like to think of time as linear. Events have beginnings and endings. Choices lead to consequences. But in a world where time loops back on itself, those assumptions crumble. Free will becomes questionable. Could the billiard ball choose not to emerge from the wormhole? Could it defy the loop? Not if the Novikov conjecture holds. Not if time enforces its own consistency. And yet there is something beautiful in the symmetry of it. In this model, the universe is not fragile, it is robust. It does not collapse under paradox, but adjusts itself to avoid one. It doesn't erase the possibility of time travel, but places guardrails around it. You can visit the past, but you cannot change it. You can interact with events, but only in ways that were always going to happen. The timeline bends, but it does not break. Still, the paradox leaves lingering questions. What happens if we push the system harder? What if we replace the billiard ball with something more complex, a human being, for example? Can a person traveling back in time interfere with their own past in a way that violates consistency? Or would their every move be subtly constrained, shaped by a timeline that loops precisely because they were always part of it? And if so, where does intention fit into that loop? Is it fate? Or is it a form of determinism written in the very structure of space-time? Polchinski's paradox is not just a quirky mental exercise, it speaks to something deeper. It shows how even the smallest, most mechanical components of reality, like a ball rolling through space, can reveal vast contradictions when viewed through the lens of time. It exposes the delicate balance between possibility and paradox, and it invites us to rethink everything we know about movement, memory, and the arrow of time. What's most intriguing is that Polchinski's scenario doesn't require any new laws of physics to exist. It plays entirely within the rules of general relativity. That means, at least theoretically, the paradox is not just possible, it is a natural consequence of how space-time behaves under extreme conditions. We may never build a working wormhole. We may never send a ball, or ourselves, through time. But the mere fact that these paradoxes can be imagined and resolved tells us that the universe is far stranger than we once believed. In the quiet of this paradox, we glimpse a universe where time is not a straight road, but a looping trail that folds in on itself. A place where events are not just sequenced, but entangled, bound together in self-sustaining rhythms. In such a world, reality becomes a puzzle box, and time, the trickiest piece of all. So the next time you hear a clock ticking, imagine not just the present fading into the future, but the future whispering back into the past. Imagine a simple ball, rolling into a wormhole, only to emerge seconds earlier and change its own path. And imagine a universe watching all of this unfold, not in confusion, but in perfect, paradoxical harmony. Black hole information paradox. Few ideas in modern physics have generated as much confusion, debate, and wonder as the black hole information paradox. It is not just a riddle buried in the heart of the cosmos, it is a direct challenge to the very foundations of how we understand reality. At the intersection of general relativity and quantum mechanics, this paradox raises a haunting question. What happens to information when it falls into a black hole? And if it truly vanishes, does that mean the universe forgets? To begin understanding the paradox, we must first grasp what a black hole is. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull. At its center lies the singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which no information can return to the outside universe. From afar, a black hole appears quiet and opaque, but in reality, it is a place of extraordinary turbulence, where space and time twist in unimaginable ways. The paradox began to take shape when physicists asked a seemingly simple question. If something falls into a black hole, where does the information about it go? In classical physics, information is preserved. If you burn a book, the pages are destroyed. But in principle, the information, the words, the ink patterns, the order, still exist in the form of smoke, heat, and ash. The universe keeps track of every detail, however complex or dispersed. This is a cornerstone of quantum mechanics, the conservation of information. It's not just a convenient rule, it's a fundamental law. But black holes pose a terrifying exception. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery. He showed that black holes are not entirely black. Due to quantum effects near the event horizon, black holes emit a faint radiation, now known as Hawking radiation. Over time, this radiation causes the black hole to shrink and eventually evaporate. This seemed like an elegant solution to the mystery of black holes, but it came with a horrifying consequence. Hawking radiation is random. It carries no information about the matter that fell into the black hole. Once the black hole evaporates completely, everything it consumed appears to be lost forever. This is the heart of the black hole information paradox. If the black hole disappears and the information doesn't escape, then it has been destroyed. But quantum mechanics insists that information cannot be destroyed. The paradox then is simple and profound. Either our understanding of quantum mechanics is wrong, or black holes don't behave the way Hawking predicted. Both options shake the very foundation of physics. For decades, the scientific community was split. Some argued that Hawking's calculation was incomplete, that somehow information must be preserved, even if we couldn't yet see how. Others took a more radical view, proposing that maybe quantum theory itself needed to be modified. Some even speculated that perhaps black holes weren't as black as they seemed, that subtle clues or faint echoes of information might escape in ways we hadn't yet detected. One proposed resolution came in the form of black hole complementarity. This idea suggests that information is both reflected at the event horizon and passes through it. To an outside observer, the information never really enters the black hole. It hovers just above the horizon and is slowly encoded in the Hawking radiation. But to an infalling observer, it continues inward. In this framework, no observer sees a violation of physics, but the two perspectives cannot be reconciled. It's as though the universe is telling two different stories at once, both true but never overlapping. Yet even this elegant solution raised difficult questions. How could a black hole radiate information if Hawking radiation is inherently thermal and random? What mechanism could imprint meaningful data into what seems like chaotic noise? And what of the firewall paradox, which suggested that if information is preserved at the horizon, then the event horizon must be a wall of searing energy, violating Einstein's predictions that falling into a black hole should be painless, at least initially. Then came a major breakthrough. In the 1990s and early 2000s, string theory and holography opened new avenues of thought. The ADS/CFT correspondence, a bold idea proposed by Juan Maldacena, suggested that everything happening inside a region of space, with gravity, could be fully described by a quantum theory on its boundary, a lower dimensional surface. This is the holographic principle. The universe, in a sense, may be like a hologram, where the information of a three-dimensional volume is encoded on a two-dimensional boundary. If black holes obey the holographic principle, then the information they contain is not lost but spread across their event horizons, like an intricate pattern on a cosmic film. The evaporation process may scramble the information, but it remains. The data that enters the black hole is encoded, however subtly, in the Hawking radiation emitted. This was a promising direction, but for years, the exact mechanism remained elusive. The math was tantalizing but incomplete. More recently, a new generation of physicists have taken up the challenge, and the pieces of the puzzle are beginning to fit together. Through detailed calculations involving quantum extremal surfaces, surfaces hidden just inside the event horizon that calculate the entanglement entropy of a black hole. Researchers have shown that the information content of a black hole appears to evolve in a way that suggests it is not truly lost. These surfaces act like accounting tools for quantum information, tracking how it escapes over time. This idea supports what's known as the page curve, a theoretical prediction that a black hole begins emitting information-rich radiation after a certain point, as it shrinks. This doesn't mean the paradox is fully resolved, but it points toward a universe that does not permit the destruction of information, even in the heart of a black hole. It suggests that black holes are not endings but transformations, cosmic crucibles where matter and information are compressed, scrambled, and eventually released. We still don't know exactly how it works. The physics remains murky at the intersection of gravity and quantum mechanics, but the outlines are becoming clearer. What makes the black hole information paradox so powerful is that it touches not just on astrophysics, but on philosophy. It forces us to ask, what is information really? Is it tied to matter or something more abstract? Can the universe know things, and can it forget? And if a single atom's position, velocity, and spin are lost forever, does that unravel the very logic that the cosmos relies on? This paradox also bridges the personal with the cosmic. Just as we wonder what happens to the things we've lost, our thoughts, our memories, the details of a moment long gone, we ask what happens when a star collapses under its own weight. Does it vanish into oblivion? Or does it carry with it some indelible imprint of what it once was? In this way, black holes become mirrors. They reflect not just light and gravity, but our deepest concerns about permanence, impermanence, and the meaning of memory. The answer to the paradox may lie in a new, unified theory of quantum gravity, something that merges general relativity and quantum mechanics into a single, elegant framework. Such a theory does not yet exist, but the information paradox is one of its loudest and most persistent invitations. It is the universe's way of telling us that something is missing from our understanding, and that the road to that understanding winds through the darkness of black holes. Until we resolve it, the paradox remains one of the most beautiful mysteries in physics. It reminds us that the universe is not just vast and ancient, but subtle and intelligent in its design. That nothing, not even light, may escape a black hole, but that perhaps, just perhaps, information does. Whispered in radiation, written in shadows, waiting to be understood. Double-Slit Experiment. Of all the experiments in the history of science, none is quite as haunting nor as enlightening as the double-slit experiment. It is in many ways the ultimate riddle of reality, a simple setup that cracks open the foundation of physics and reveals a world stranger than we ever imagined. Conducted over 2 centuries ago and repeated in countless forms since, the double-slit experiment forces us to ask a question that has no easy answer. What is the nature of matter? And what role do we, the observers, play in shaping it? Imagine a wall with 2 vertical slits carved into it, like narrow windows to the unknown. Behind the wall is a screen that records impacts, and in front of it, a source, be it a gun firing bullets, a hose spraying water, or, in our case, a machine that emits particles of light known as photons. The goal is simple: fire particles at the slits and see what lands on the screen. Logic tells us this is straightforward. If you shoot a series of bullets at the wall, some will pass through the left slit, some through the right, and the pattern that forms on the back screen will be the sum of those 2 shapes, 2 bands: predictable, sensible, mechanical. But light is not so simple. When light is passed through the double slits, it doesn't form 2 distinct bands. Instead, it creates an interference pattern, dark and bright fringes spaced out across the screen, like ripples in a pond colliding and amplifying or canceling each other. This is the signature of a wave, not a particle. It tells us that the light did not go through one slit or the other. It went through both simultaneously and interfered with itself. The light behaved as if it were a wave that split, passed through both slits, and then recombined on the other side. But here's where it gets truly strange. Fire individual photons, just one at a time, and you still get the same pattern over time. Each photon seems to interfere with itself, as if it knows the layout of the experiment, as if it goes through both slits at once. But how can a single photon, a single particle, take 2 paths? It should go through one or the other, not both. Particles are supposed to be discrete, localized objects. Waves are supposed to be spread out, continuous. But here, in this simple experiment, light defies both categories. It behaves as though it is both and neither. So, the scientist asked the next logical question: what if we watch? What if we place a detector at the slits to see which path the photon actually takes? Surely that will clarify the mystery. So they do. And what happens? The interference pattern disappears. The photon behaves like a regular particle. 2 simple bands emerge. The mystery dissolves until you turn the detector off. Then, the interference pattern returns. This is the shock at the heart of the double-slit experiment. The act of observation changes the outcome. Merely knowing which path the photon takes alters its behavior. When we observe, the wave collapses into a particle. When we don't, it remains in a state of possibility, a ghostly superposition of all paths at once. It's not just light that behaves this way. Electrons, atoms, even large molecules, when passed through double slits, show the same interference patterns. All matter, at a fundamental level, seems to possess this dual identity: wave and particle, probability and precision. Reality itself seems to remain in a suspended state until we, the observers, interact with it. Our curiosity, the mere act of looking, pulls the quantum world into focus. This revelation sent shock waves through physics. It was more than a curiosity. It was a philosophical upheaval. It suggested that reality is not fixed, not absolute, not entirely objective. It dances on the edge of potential until attention snaps it into place. Niels Bohr and Werner Heisenberg, pioneers of quantum theory, embraced this strange conclusion. They developed the Copenhagen interpretation, which states that quantum systems remain in a state of superposition, existing in multiple possibilities until measured. Measurement collapses the wave function. In other words, observation creates the outcome. Albert Einstein famously objected, He could not accept a universe governed by chance and shaped by observation. God does not play dice, he declared, but experiment after experiment confirmed the quantum view. The double-slit experiment became the cornerstone of this new understanding, a gateway into a world where uncertainty reigns, where particles are smeared across space until forced to choose, and where the boundary between subject and object begins to blur. Even more unsettling are the experiments that delay the decision. In the delayed choice version of the double-slit experiment, scientists set up a scenario where the decision to observe the photon's path is made after it has already passed through the slits. The outcome? The same as before. If you observe, you get 2 bands. If you don't, you get interference. The photon's behavior seems to depend on something that happens in the future. It's as if the particle knows whether it will be observed and adjusts its behavior accordingly, retroactively collapsing its path. This challenges not only our understanding of particles and waves, but of time itself. It suggests that cause and effect might not flow in a straight line, that the future can shape the past, that observation can ripple backward, rewriting history in quiet, invisible ways. It leaves us with a chilling implication. Reality is not merely watched, it is woven by observation. The observer is not outside the system, they are part of the system. And the system behaves differently depending on whether someone is watching. This brings us to a deeper mystery. What exactly is an observer? Is it any measuring device? Is it a conscious mind? Is it a camera, a sensor? The line between inanimate measurement and conscious observation remains blurry. Some interpretations suggest that consciousness itself is the true catalyst, that the mind, by witnessing, brings the universe into being. Others recoil from this notion, preferring to believe that the wave function collapse occurs through physical interaction alone. But the question remains open. At the core of quantum mechanics lies not just a scientific problem, but a philosophical one. What is the role of the mind in reality? Some interpretations, like the many worlds theory, try to avoid collapse altogether. In this view, every possible outcome happens. When a photon hits the slits, it takes every path, one in each universe. The universe splits, branches, and multiplies infinitely and eternally. In one branch, the photon goes left, in another, right. In yet another, it does both. Observation doesn't collapse reality, it merely places us in one of countless versions of it. It's an elegant idea, but it comes at a price. The loss of uniqueness, the endless birth of invisible worlds, and a dizzying sense that reality is far more crowded than we thought. Still others embrace the pilot wave theory, suggesting that particles follow precise paths, guided by hidden variables, a wave of potential that flows beneath the surface. This interpretation preserves determinism and avoids the idea of magical wave function collapse, but it remains on the fringe, never quite dethroning the Copenhagen view that has ruled for a century. What makes the double-slit experiment so enduring is its simplicity. It does not require vast machinery or colliders buried underground. It does not demand exotic particles or extreme energy, just a source of light, 2 slits, and a screen. And yet, in that quiet space between slits, the universe reveals its deepest secrets. It tells us that matter is not matter as we once understood it, that observation is not passive, that the world is not made of tiny indivisible things, but of probabilities, possibilities, and mysteries we are only beginning to grasp. And perhaps that is the most important lesson of all. The double-slit experiment reminds us that reality is not something cold and fixed, but something dynamic, shifting, alive. It invites us to participate, not as distant spectators, but as integral parts of the unfolding story. Every observation we make is a thread woven into the fabric of existence. Every measurement, a decision. Every moment, a choice between the known and the unknown. We may never fully solve the riddles it presents. We may never agree on what they mean. But the double-slit experiment will endure, silent, simple, and infinite in its implications. It will remain the gentle doorway through which we glimpse the true strangeness of the quantum world, and every time we pass through it, we find ourselves asking the same question: what really is real? Olbers Paradox. At first glance, the world seems solid, stable, and predictable. We look at a tree and we believe it's there whether we observe it or not. We hear a sound and assume it had a source, whether or not we noticed it right away. We believe in an objective universe, a cosmos that exists independently of our minds. But the deeper we look, especially through the lens of quantum physics, the more this comfortable illusion begins to unravel. And at the center of this unsettling realization lies the Olbers Paradox, the baffling idea that the act of observation can alter the thing being observed. This paradox does not begin in a laboratory filled with machines and equations. It begins with a simple question that ripples through science and philosophy alike. Can we study something without changing it? In classical science, the answer seems to be yes. You can weigh an object without changing its mass. You can measure a planet's orbit without disturbing its path. You can record the temperature of a pot of water without affecting the heat itself, at least not significantly. But when we shrink the scale, when we dive into the realm of the very small, the subatomic world of particles and waves, things begin to behave differently. Suddenly, the very act of measuring, of watching, of noticing, becomes intrusive. In the world of quantum mechanics, particles like electrons and photons do not have definite positions or velocities until they are measured. Before observation, they exist in a state of probability, a haze of potential outcomes known as a wave function. It's not that the particle is here or there, it's that it is both, or more accurately, it exists in all possible states simultaneously. This is called superposition, but the moment we measure it, the wave function collapses, the haze clears, the particle chooses. It decides to be in one location or one state and not in the others. And what triggers this collapse? Us, the observer. This is the heart of the Olbers Paradox. It is not just that we see the universe, it's that our seeing seems to create the universe we see. The measurement does not merely reveal a pre-existing reality, it appears to bring one into being. In other words, the observer does not passively reflect reality, but actively shapes it. This idea is not just unsettling, it's revolutionary. It implies that the universe is not fully formed without us. That matter at its most fundamental level does not behave objectively, but subjectively, responding to the presence of a watcher. Of course, the implications of this are staggering. If observation determines reality, then what is the role of consciousness? Is it possible that the universe requires a mind to exist in a particular state? Are we simply measuring instruments of reality or participants in its creation? This is where quantum physics becomes metaphysical. The boundary between science and philosophy begins to dissolve, and we are left with questions that echo far beyond the laboratory. One of the most famous illustrations of this paradox is Schrödinger's cat, a thought experiment proposed by Erwin Schrödinger to highlight the strangeness of quantum superposition. In the experiment, a cat is placed inside a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the poison is released and the cat dies. If it doesn't, the cat lives. But according to quantum theory, until the box is opened, until the system is observed, the atom exists in a superposition of decayed and not decayed, and therefore, so does the cat. It is simultaneously alive and dead. Only when we look does the cat become one or the other. The observer defines the outcome. Now, let's bring this back to real-world physics. In the famous double-slit experiment, light or matter is fired at a screen through two slits. When unobserved, the particles behave like waves, creating an interference pattern on the screen, suggesting they went through both slits. But the moment we measure which slit the particle goes through, the pattern changes. The wave collapses. The particle picks a slit. The act of observing alters the behavior of the particle, erasing the interference pattern entirely. The presence of an observer changes the outcome of the experiment, not by force, not by intention, but simply by existing. The paradox deepens when we consider what counts as an observation. Is it a human eye watching a particle? Is it a mechanical device recording a result? Is it a conscious mind aware of an outcome? The scientific community remains divided. Some physicists argue that any interaction, any entanglement with another system, constitutes a measurement. Others believe that only conscious awareness can collapse the wave function. This leads to a more philosophical version of the paradox. If a tree falls in a forest and no one is there to hear it, does it make a sound? Quantum mechanics suggests that the answer might be no, not until someone observes it. Even in fields outside of physics, the observer's paradox makes an appearance. In social science, for example, the presence of an observer can change people's behavior. Known as the Hawthorne effect, it describes how individuals may alter their actions simply because they know they're being watched. This phenomenon is not limited to particles. It lives in our everyday interactions, in how we perform under a camera, in how people act in public versus private, and even in how we perceive ourselves. But the quantum version is far stranger. It doesn't just suggest that people change their behavior when observed. It suggests that the universe changes its behavior. The paradox transforms the observer from a passive witness into a co-creator of reality, and it forces us to reimagine our place in the cosmos, not as outsiders looking in, but as active participants, entangled with the fabric of what is. Some interpretations of quantum mechanics, like the Copenhagen interpretation, embrace this observer-dependent view. Others, like the many worlds interpretation, try to bypass the paradox entirely by proposing that every possible outcome occurs in a branching multiverse. In this view, the observer doesn't collapse the wave function, they simply become entangled with one outcome in a branching universe of all outcomes. Still, the role of the observer remains central. Whether we cause collapse or navigate possibility, we are inseparably linked to the unfolding of the quantum world. What does this mean for reality, for truth, for the idea of an objective world that exists regardless of who's watching? The observer's paradox challenges the classical worldview, the Newtonian dream of a clockwork universe ticking along with no regard for human thought. Instead, it offers a vision of reality that is dynamic, participatory, and deeply interwoven with the presence of awareness. This does not mean that the universe is a projection of our minds. It doesn't mean that nothing exists until we look. Rather, it means that at the deepest level, the relationship between observer and observed is not passive but active. The fabric of the cosmos may be sensitive to interaction, and that interaction, subtle, unspoken, and often unintentional, might shape what we call existence. In the end, the observer's paradox is not just a puzzle of particles and wave functions, it is a doorway into a new way of seeing. It invites us to pause, to consider the quiet but profound power of attention. It reminds us that to look is to touch, that to measure is to mold, and that even the smallest glance carries with it a ripple that echoes through the quantum field. We are not outside the story of the universe. We are written into its equations, folded into its probabilities, inscribed into the patterns of light and matter. The paradox may never be fully resolved. It may always remain a reminder that reality is more subtle than certainty allows. But in its mystery, we find something extraordinary. The possibility that the universe is not just a place we observe, but a conversation we are always part of. Quantum suicide paradox. In the quiet realm of quantum physics, there exists a thought experiment so unnerving, so psychologically intimate, that it blurs the boundary between science and philosophy, between life and death, and between what we believe and what reality might actually be. It's called the quantum suicide paradox. Unlike other paradoxes that deal with distant stars, abstract particles, or theoretical equations, this one turns the lens inward, on consciousness, identity, and mortality itself. It's not a story about the universe in general, it's about you. and it begins with a simple, if unsettling, question: what would it feel like to die in a multiverse? The roots of this paradox come from one of the most radical interpretations of quantum mechanics, the many worlds interpretation. Proposed by physicist Hugh Everett in 1957, the theory suggests that every possible outcome of a quantum event actually happens, but in a different branch of the universe. When a quantum decision is made, reality does not collapse into one outcome, it splits, branching into multiple versions, each just as real as the one we perceive. In one, the cat lives, in another it dies. In one, the photon goes left, in another it goes right. There is no collapse of possibility, there is only expansion. The quantum suicide thought experiment builds directly upon this interpretation. Imagine a scientist, let's call him the observer, who builds a quantum-based version of Russian roulette. He connects a quantum particle, such as a spin or a decay event, to a device that either kills him or spares him, depending on the outcome. If the quantum state measures up, the gun clicks harmlessly. If it measures down, it fires. In the classical view, this is simply a matter of probability. Over time, the scientist will eventually die, just as someone flipping a coin 1,000 times will eventually hit a fatal combination. But in the many worlds view, something stranger happens. Every time the trigger is pulled, the universe splits. In one universe, the gun fires and the observer dies. In another, the gun clicks and he survives. From an outside perspective, both outcomes occur, and both observers exist in their respective branches. But from the point of view of the observer who survives, there is a persistent experience of survival, no matter how unlikely it becomes. Over and over, he continues to exist in the branch where he lives. To him, the gun never fires. He becomes, in essence, immortal, surviving against all odds in an ever-thinning sliver of the multiverse. This is the paradox. Quantum suicide suggests that you could never experience your own death. In any scenario where death is determined by quantum randomness, there will always be at least one branch of the universe where you survive, and that is the only branch your consciousness will experience. To others, you might be dead 1,000 times over, but from your perspective, you live on, again and again. Through the abyss, into a world like Idias, no matter what. This is called quantum immortality, and it leads to some of the most bizarre and chilling conclusions in theoretical physics. It's important to clarify that this idea doesn't imply physical invulnerability in the real world. It doesn't mean you can walk into traffic or leap off buildings and expect to survive in all universes. It only applies to situations where death is tied to a quantum outcome, a fundamentally random, unmeasured event like the decay of a particle or the spin of an electron. The paradox arises from the assumption that your consciousness only follows the path where it remains intact, and because consciousness can't experience its own non-existence, you are never aware of the branches in which you die. But this line of thinking leads us into philosophical territory that's difficult to escape. What exactly is consciousness in a multiverse? If you are split into multiple versions with each quantum decision, then who are you? Is the you that survives the same person as the one that would have died? Or are they divergent beings, each carving their own path through an ever-branching sea of realities? Does personal identity persist through these quantum bifurcations? Or does it fragment, dissolving into the chaos of infinite possibility? And what of morality? If in some universe every outcome happens, does choice still matter? If every version of you exists, every selfish one, every noble one, every victorious and every tragic, does anything you do carry weight? Or is this branching structure simply a backdrop, while your conscious stream clings to one narrow thread through the web of potentiality? These are not questions with easy answers. They are, in fact, the kinds of questions that unsettle the soul. The quantum suicide paradox is not just a scientific curiosity. It is a mirror held up to human vulnerability, to our fear of death, to our search for permanence. It tempts us with the idea that maybe we do not truly die, that somewhere in some distant branch of the multiverse, our story goes on. that we awaken in a hospital bed after the accident, that the diagnosis was wrong, that the bullet missed. It whispers the promise of survival, of continuity, of escape. But at what cost? Because this immortality is not peace. It is not freedom from pain. It is survival in the most literal and relentless sense. As other branches fall away, you continue in the ones where you endure. That might mean waking up paralyzed. It might mean growing older while the people you love fade away in other branches. It might mean being the last flicker of a consciousness clinging to a broken body in a decaying universe. Quantum immortality is not heaven. It may be a curse. The thought of never dying becomes, in some interpretations, the thought of never being allowed to die. It also brings us back to the question of observation. In quantum physics, the role of the observer is pivotal. The act of measuring a quantum system determines its state, but in quantum suicide, the observer and the observed are the same. You are both the subject and the instrument. Your survival becomes the measurement, and your consciousness the result. This self-referential loop adds another layer of strangeness to an already surreal idea. It makes death not just a biological process, but a quantum event, experienced or not, depending on which thread of the multiverse your awareness follows. Critics of the paradox argue that it stretches the interpretation too far, that while the math of many worlds holds up, the philosophical leap to consciousness continuity is unfounded. After all, we don't know how consciousness arises. We don't know if it can split or if it is confined to one timeline. Some scientists dismiss the idea entirely, calling it a misapplication of quantum theory to domains it was never meant to describe. Others see it as a natural, if uncomfortable, consequence of taking the many worlds interpretation seriously. Whether literal or metaphorical, the quantum suicide paradox has become one of the most provocative thought experiments in modern science. It pushes us to confront the limits of our understanding, not just of physics, but of self. It asks us to imagine a universe where nothing is ever truly lost, where every outcome plays out somewhere, and where the thread of consciousness winds endlessly through an infinite landscape of branching realities. And yet, despite its strange beauty, most of us live in the classical world. We experience one life, one death, one story unfolding in time. We make choices, we feel their consequences. We fear death not as a quantum event, but as a final moment, irreversible and silent. The paradox may hint at other worlds, but it is in this world that we love, grieve, and find meaning. Still, the paradox lingers. Like a whisper in the background of reality, it reminds us that the universe is more mysterious than we know, that the nature of life and death may not be as simple as it seems, that somewhere, perhaps, in a version of reality where chance favored you, you are still alive, reading these words, still wondering. Twin paradox. The universe does not move at a steady pace. Time, we often assume, ticks forward at the same rate for everyone, everywhere, regardless of their motion or surroundings. But that assumption is an illusion, one that breaks down under the lens of relativity. Nowhere is this more clearly illustrated than in the famous thought experiment known as the twin paradox. It's a story about two siblings, identical in every way except for the journey one of them takes. A story where time itself becomes uneven, and where the deeper we look, the more we find time to be not a fixed current, but a river that bends, stretches, and flows differently depending on where you stand. Imagine two twins. Let's call them Alex and Sam. They are born together, grow up together, and at a certain point, Sam decides to embark on a space voyage. Sam boards a spaceship capable of near light-speed travel and sets off toward a distant star, thousands of light years away. Alex remains on Earth. For Sam, the journey is intense. The spaceship accelerates rapidly, reaches a high speed close to the speed of light, coasts through the darkness, then turns around and makes the return journey. Years pass, but not equally for the two twins. When Sam returns home, a shocking discovery awaits. Alex has aged far more than Sam. One twin is now old, the other is still young. This is the twin paradox. It is not a contradiction of physics, but a consequence of it. It arises directly from Einstein's special theory of relativity, which tells us that time is not absolute. Instead, time is relative. It flows differently for observers who are moving at different velocities. The faster you travel, the slower time moves for you relative to someone who is stationary. This effect, called time dilation, has been measured and confirmed in countless experiments. It's not hypothetical, it's real, and yet it remains profoundly strange. In the twin paradox, Sam's time flows more slowly than Alex's because Sam is the one moving rapidly through space. But at first glance, the situation seems symmetrical. Couldn't Sam argue that it was Alex who moved away and Sam who remained still? After all, in space there is no absolute rest, only motion relative to other objects. This is where the paradox seems to emerge. If all motion is relative, why should one twin age differently than the other? The resolution lies in the fact that the situation is not truly symmetrical. Sam's journey involves acceleration and deceleration, speeding up, turning around, and slowing down, while Alex's does not. Sam's path through space-time is different. In the language of relativity, Sam's trajectory involves changing frames of reference, while Alex remains in the same inertial frame the whole time. The moment Sam turns around to head back toward Earth, the symmetry breaks. That change in direction introduces an asymmetry, and it is this asymmetry that causes the difference in aging. To understand why time slows down for Sam, we must delve deeper into the heart of special relativity. At its core is the idea that the speed of light is constant for all observers, no matter how fast they are moving. This simple postulate has profound consequences. If the speed of light must remain the same, then measurements of time and space must adjust to preserve that constancy. Moving clocks run more slowly, distances contract in the direction of motion, and simultaneity, the idea that two events occur at the same time, becomes relative. What is simultaneous for one observer may not be for another. For Sam, aboard the spaceship, time passes normally. A clock on the ship ticks at its usual rhythm. Sam eats, sleeps, reads, and dreams without any sensation that time is moving unusually. But compared to Earth, that clock ticks slowly. To Alex, Sam's heart beats more slowly, the ship's clocks move sluggishly, and Sam appears to age at a crawl. When Sam returns, it is not simply that Earth has moved forward in time, it is that Sam has moved through less time. The journey through space became a shortcut through time. This effect has been measured in real life. Astronauts on the International Space Station, orbiting Earth at high speeds, experience time slightly more slowly than people on the ground. The difference is tiny, fractions of a second, but measurable. Atomic clocks flown on airplanes return slightly behind those left on Earth. GPS satellites must account for both special and general relativistic effects to maintain accurate timing. The twin paradox, though dramatic in its thought experiment form, is grounded in observable reality. But the paradox also reveals something deeper, a philosophical unease about the nature of time. We are used to thinking of time as a shared experience, a rhythm we all march to equally. The twin paradox shatters that notion. It tells us that time is personal, local, dependent on motion and gravity. Each of us carries our own clock, and those clocks can drift apart depending on the paths we take through space-time. The more extreme those paths, closer to the speed of light or deeper in a gravitational well, the more our timelines diverge. In this sense, the twin paradox is not just about twins. It's about the fragility of time itself, about how experience and duration are not universal truths, but intimate companions of motion and mass. It suggests that the universe has no single now, only an endless patchwork of nows, stitched together by light and observation. The present, like the past and future, is relative. It also offers a glimpse into time travel, not the fantastical kind with machines and wormholes, but the real, physical kind permitted by relativity. If Sam could travel close enough to the speed of light, Earth might experience centuries while Sam experiences only years. Sam could leap forward in time, skipping eras of history, returning to a future unrecognizable. But this time travel has a cost. It is one way. There is no return to the past, no undoing of the journey. It is a path paved by velocity and isolation. Some find this idea exhilarating. Others find it lonely. The twin paradox is, at its core, a human story. One twin leaves, the other stays. One returns to find their sibling aged, their home changed, the world moved on without them. It's a story of separation, of reunion, of the irreversible nature of time. It reminds us that while physics can bend time, it cannot erase the emotional weight of its passage. In the end, the twin paradox teaches us that time is not what we thought. It is not an invisible drumbeat that guides the universe. It is not a cosmic metronome ticking in the background. Time is woven into space, into speed, into the fabric of reality itself. It is elastic, it is relative, and it is, perhaps, more mysterious than anything else we know. So when we look up at the stars, imagining ships that travel between them, we must also imagine the clocks aboard those ships ticking differently. We must imagine the astronauts returning to find a world that has grown old while they have remained young. And we must remember that time, like the stars themselves, is not fixed in place, but ever-changing, depending on how we move through it. Banach-Tarski Paradox. In a universe governed by logic and reason, some ideas slip quietly through the cracks, paradoxes that do not scream their confusion but instead sit quietly, unsettling the very framework beneath our understanding. The Banach-Tarski Paradox is one such idea. It is not born from black holes or quantum uncertainty. It is not a question about consciousness or death. Instead, it arises from the seemingly solid, dependable world of mathematics, from the abstract yet orderly realm of geometry and set theory. And yet, it presents a conclusion so absurd, so impossible sounding, that it threatens to dissolve our trust in the coherence of space itself. In essence, the Banach-Tarski paradox says this: it is possible to take a solid ball, cut it into a finite number of pieces, and reassemble those pieces, without stretching or distorting them, into two solid balls of the same size as the original. One ball becomes two. No tricks. Just math. At first glance, this sounds like a magician's sleight of hand, like some conjuring illusion wrapped in formal language. But this is not an illusion. It is a proven theorem, derived from the foundations of set theory and the properties of infinite sets. The Banach-Tarski paradox is not a suggestion or a hypothesis, it is a mathematical certainty, as rigorously defensible as the Pythagorean theorem, and that is precisely what makes it so disturbing. The paradox was first proposed in 1924 by two Polish mathematicians, Stefan Banach and Alfred Tarski. Working in the early days of modern set theory, they sought to explore how rigid geometric objects behave under the rules of mathematical logic, particularly when those rules permit the existence of certain non-measurable sets. These are sets that cannot be assigned a consistent volume using traditional notions of geometry. They are not exotic objects hidden in distant corners of the universe. They are baked into the very fabric of mathematical space, lurking quietly behind the scenes of even the most basic shapes. To understand the Banach-Tarski paradox, you must let go of physical intuition. This is not a problem of matter, of molecules, or even of real-world objects. It is a problem of infinite precision, of slicing objects into infinitely small, infinitely complex pieces that cannot be visualized or built, only imagined and described using pure logic. The pieces used in the Banach-Tarski construction are not ordinary slices. They are not like pieces of a pie or shards of broken glass. They are deeply non-intuitive fragments, constructed using the axiom of choice, a controversial but widely accepted principle in modern mathematics that allows for the selection of elements from an infinite collection of sets. even when no explicit rule for selection is provided. With the axiom of choice in hand, Banach and Tarski showed that a three-dimensional ball can be divided into just 5 specific pieces. These pieces are then moved, rotated, and reassembled, without any stretching, duplication, or change in shape, into 2 balls identical in size to the original. No mass is added, no space is created, yet the result is duplication. 1 becomes 2, and not just approximately, exact perfect duplicates derived from a single source. How is this possible? The key lies in the strange properties of infinite sets and the way they behave under certain transformations. In the world of infinity, our everyday expectations fall apart. In finite mathematics, doubling something means adding more. But in the realm of the infinite, you can split, rearrange, and duplicate without breaking any rules. The paradox exploits this, creating a situation where the volume of an object is no longer preserved because the pieces are so wildly fragmented that they defy standard definitions of volume altogether. But what makes the Banach-Tarski paradox more than just a mathematical curiosity is what it suggests about the nature of reality. If the rules of mathematics, our most trusted language for describing the world, allow for such bizarre outcomes, what does that say about the universe those rules are meant to model? Could space itself be infinitely divisible? Could objects be broken and reassembled in ways that multiply mass? Of course, in the physical world, such a duplication is impossible. Atoms cannot be sliced into infinite pieces. Matter cannot be restructured without limits. The paradox lives purely in abstraction, yet it haunts the edge of reality, whispering possibilities that reason rejects but logic permits. Physicists are quick to point out that the Banach-Tarski paradox has no real-world counterpart. The construction relies on pieces that are not physically realizable. They cannot be built, touched, or even fully described. They exist only as logical entities, as constructions allowed by the axiom of choice. In practical terms, the paradox cannot be performed, but in theoretical terms, it is unshakable. It is as true as any mathematical proof can be. And in this lies the paradox's power. It reveals the strange gap between mathematical truth and physical reality. The paradox also raises uncomfortable questions about the foundations of mathematics itself. The axiom of choice, while essential to many branches of modern mathematics, is not universally accepted. Some mathematicians prefer to avoid it because of the strange, often counterintuitive results it produces, Banach-Tarski being the most famous. Without the axiom of choice, the paradox collapses. With it, the paradox stands. So what do we do with a mathematical principle that is both powerful and paradoxical? We accept it, usually because it works. But we do so with unease. In a way, the Banach-Tarski paradox is less about cutting spheres and more about cutting through certainty. It is a reminder that logic, no matter how rigorous, can lead us to conclusions that defy our instincts. That mathematics, for all its clarity, contains shadows. It is not a glitch in the system, it is the system, a window into the profound weirdness that lies beneath the surface of reason. Some have compared the paradox to magic, others to alchemy, but in truth it is something deeper. It is the revelation that even our most trusted structures of thought contain mysteries we cannot resolve. It is the mathematical equivalent of dreaming while awake, of discovering a loophole in the rules of the universe, even if it exists only on paper. It reminds us that the boundary between the logical and the absurd is not always as firm as we believe. At its heart, the Banach-Tarski paradox is a meditation on the infinite. Infinity is not just a large number. It is a fundamentally different kind of quantity, one that obeys its own rules, resists intuition, and reshapes our understanding of what can and cannot be. In the infinite, duplication is not magic, it is structure. It is possibility, and it is precisely these strange properties that the paradox illuminates. In the end, we return to the beginning, a simple sphere resting in space. We slice it, carefully, abstractly, impossibly. We move the pieces, we reassemble, and from one ball, two emerge. Not because we cheated, but because we followed the rules. And that, perhaps, is what makes the Banach-Tarski paradox so unforgettable. It is not an error in reasoning. It is reasoning, carried to its extreme. It shows us that even in the purest of logical spaces, the impossible may be not only possible, but inevitable. Schrödinger's cat. In the shadowy world of quantum mechanics, few thought experiments are as famous or as misunderstood as Schrödinger's cat. First proposed in 1935 by Austrian physicist Erwin Schrödinger, this paradox was not intended to explain quantum mechanics, but to expose its absurdity when stretched into the domain of everyday life. It is a story where a cat becomes the protagonist of a quantum fable, where the line between life and death blurs into uncertainty, and where reality itself seems suspended in a fog of probabilities. The image is simple, yet disturbing. A sealed box, a live cat inside, and a mechanism tied to a random quantum event. And from this simplicity emerges one of the most profound philosophical puzzles in modern physics. The setup begins with a cat placed inside a closed box, hidden from view. Alongside the cat is a small container of radioactive material, a Geiger counter, a vial of poison, and a hammer poised to shatter the vial. The radioactive material is rigged so that within 1 hour there is a 50% chance it will emit a particle and a 50% chance it will not. If the Geiger counter detects a decay particle, it triggers the hammer, which smashes the vial, releasing the poison and killing the cat. If no particle is detected, nothing happens and the cat survives. From the perspective of quantum theory, the radioactive particle exists in a superposition. It has both decayed and not decayed. And therefore the cat, tied to the outcome of that event, is also in a superposition, both alive and dead, until someone opens the box and observes the outcome. This idea is unsettling not because it involves death, but because it forces us to question what it means to know something. According to the traditional interpretation of quantum mechanics, known as the Copenhagen interpretation, a quantum system does not have a definite state until it is observed. The wave function, which describes all the possible outcomes of a system, remains in a state of superposition until a measurement collapses it into one reality. Schrödinger's cat takes this to a terrifying conclusion, that macroscopic objects, like cats or even people, could exist in limbo states, suspended between contradictory outcomes until the moment of observation. But Schrödinger's true aim was to highlight the absurdity of this logic. He did not believe the cat was literally both alive and dead. His paradox was a critique, not a belief. He was pointing out that if we follow the logic of quantum mechanics blindly, it leads us to conclusions that violate our common sense. It suggests that the act of observation is not just about uncovering reality, it is about creating it. That the cat's fate is not decided when the radioactive particle decays, nor when the poison is released, but only when someone finally opens the box and looks inside. This challenges one of the most basic assumptions in science, that reality exists independent of whether we are observing it. The Schrödinger's cat paradox suggests otherwise. It implies that until we look, the world does not commit to a single outcome. It exists as a cloud of possibilities, a blend of contradictory truths, a probabilistic dream waiting to collapse into a single waking reality. This leads to an even deeper question. What exactly constitutes an observation? Is it a conscious human mind? Could it be a camera, a sensor? Or does the mere interaction between particles, entanglement, measurement, and collapse, count as observation, regardless of who is watching? Different interpretations of quantum mechanics offer different answers. Some argue that any interaction that disturbs the system is enough. Others suggest that conscious awareness is required to finalize the outcome. And still others, like the many worlds interpretation, sidestep collapse entirely by proposing that all possible outcomes happen, each in its own branch of the universe. In the many worlds view, the cat is not both alive and dead in the same world. Instead, the universe splits the moment the quantum event occurs. In one branch, the particle decays, the poison is released, and the cat dies. In another, the particle does not decay, the poison stays sealed, and the cat lives. Each possibility becomes its own reality, and both continue to evolve independently. From the perspective of an observer, once the box is opened, they become entangled with one of those branches, but both outcomes still exist. Nothing collapses. Reality just divides. Yet even in this model, the mystery remains. What is it about our experience that feels so singular? Why do we see one outcome and not the other? Why does the world appear stable, definite, and solid when beneath the surface it is anything but? Schrödinger's cat invites us to step into that ambiguity. To live, if only for a moment, in the space between states. To imagine that reality is not a single path, but a forest of overlapping possibilities, and that we walk only one narrow trail through it. There is also a deeper psychological aspect to the paradox. The cat becomes a symbol not just of quantum uncertainty, but of the uncertainty we carry within us. In life, we are often Schrödinger's cat, waiting on decisions, on diagnoses, on test results and outcomes we cannot yet see. We live in states of emotional superposition, both hopeful and afraid, both expecting the best and fearing the worst. Until the moment of revelation, we exist in that tense ambiguity. The unopened box becomes a metaphor for every unanswered question we carry, and the observation becomes the moment that reality, with all its weight, comes crashing down. For this reason, the paradox has transcended its scientific roots. It appears in literature, in film, in popular culture, and in personal conversations. People refer to Schrödinger's cat not only in physics discussions, but when talking about relationships, decisions, and emotional states. It has become a symbol of liminality, a name for the uncertain space between knowing and not knowing, between reality and imagination. But from a scientific perspective, Schrödinger's cat continues to be a powerful tool for exploring the limits of quantum theory. It reminds physicists that the quantum world does not end at the microscopic level. The rules that govern particles also apply to larger systems. The boundary between the quantum and classical worlds is not clear-cut. Experiments with increasingly complex systems, molecules, superconducting circuits, and even small biological organisms have shown evidence of quantum behavior at larger scales. The cat-in-the-box scenario, while idealized, is not entirely out of reach. And so the question remains, when does the quantum world give way to the classical world we know? At what scale does superposition vanish and definiteness take over? Is there a threshold, a dividing line, a mechanism that transitions us from the strange to the stable? Or is the entire universe one grand quantum system, and we are simply playing our part in the unfolding of its probability? Schrödinger's cat does not answer these questions. It poses them. It stretches the boundaries of thought, challenging us to confront the paradoxes that lie at the heart of the very reality we inhabit. It invites us to question what it means to observe, to know, and to exist. And it reminds us that science is not just a collection of facts and formulas, but a journey into the unknown, a dance with mystery, paradox, and the poetic strangeness of truth. In the end, the cat in the box is not just a cat, it is a mirror. It reflects our assumptions, our fears, and our relentless quest to understand. It asks us whether reality is something we uncover or something we shape by looking. It blurs the line between the observer and the observed, and it whispers a truth that is as humbling as it is profound, that certainty may be an illusion, and that the world, in its deepest form, is far more strange and wondrous than we ever imagined. Delayed choice quantum eraser. At the strange edge where physics begins to resemble philosophy, there exists an experiment so haunting, so profound in its implications, that it seems to call into question the very nature of time itself. It's called the Delayed Choice Quantum Eraser Experiment. a refinement of the already puzzling double-slit experiment, it proposes a radical idea that the decision to observe something now can influence what already happened, that somehow our choices in the present might reach backward into the past and alter reality's history. It sounds impossible. It sounds like science fiction. And yet, it is grounded in solid experimental results, repeated and confirmed. It is one of the most unsettling phenomena in quantum mechanics, and one of the most beautiful. To understand the delayed choice quantum eraser, we must begin with its predecessor, the classic double-slit experiment. When particles such as photons or electrons are fired toward a screen with two slits, they behave not as tiny localized bullets, but as waves. If both slits are open, the wave passes through both, interferes with itself, and forms an interference pattern, a series of light and dark bands on the detector screen. It is the hallmark of wave behavior, but if we try to measure which slit the particle goes through, the interference pattern vanishes. The particle behaves like a particle. The very act of observation collapses its wave-like nature and forces it into a singular particle-like path. We don't just observe reality, we change it by observing. This already presents a challenge to our classical understanding of the world, but the delayed choice version takes it further. Proposed by physicist John Archibald Wheeler, the idea was to delay the decision to observe the particle's path until after it had already passed through the slits. In other words, what if we decide whether to observe the particle after it has already chosen its behavior? If we choose to observe its path, we see it act like a particle. If we don't, we see the interference pattern. But here's the paradox. It seems as though the particle knows whether it will be observed, even if that decision is made after the fact, as if the future is reaching into the past to influence the outcome. But the story becomes even more eerie with the introduction of the quantum eraser, an experiment first performed in the late 1990s by physicist Yoon-Ho Kim and colleagues. It builds on Wheeler's idea and introduces another quantum phenomenon: entanglement. Entanglement occurs when two particles become linked such that the state of one instantaneously affects the state of the other, no matter how far apart they are. It is the universe's way of saying, these two things are no longer separate. They are parts of a single system. In the quantum eraser setup, a photon passes through a double-slit apparatus, but is then split into two entangled photons. One photon, the signal photon, continues to a detection screen where it forms a pattern. The other, the idler photon, is routed through a series of mirrors and beam splitters and is eventually measured in a way that either preserves or erases information about which slit the original photon passed through. Crucially, the path of the idler photon is long enough that the signal photon hits the detection screen before the idler is measured. In essence, we are determining whether we preserve or erase which path information after the detection has already occurred. What happens is astonishing. When we look only at the subset of signal photons whose idler partners had their which path information erased, we see an interference pattern, as if the photon had gone through both slits. But when we look at the subset of signal photons whose idlers preserved the which path information, we see no interference pattern, just two particle-like bands. This seems to imply that the decision to preserve or erase information about the idler retroactively changes how the signal photon behaved, even though it had already been detected. It is as if the past remains unresolved until the future makes a decision, as if reality does not commit to a single story until all pieces of the puzzle, past, present, and future, are brought together. Time, in this interpretation, is not a one-way street. It is a web of interactions, where effects and causes may not be so neatly divided. The observer's choice, made now, ripples backwards, altering what was. But what is really happening here? Does the future actually change the past? Not quite, at least not in a way that violates causality or allows time travel in the science fiction sense. The experiment does not allow us to send messages back in time or change known events. What it does reveal is that the quantum world is holistic. The outcome of a quantum event is not determined until the entire context, including future measurements, is known. This is why the full interference pattern only emerges when the data from the signal and idler photons is combined. Until then, each photon seems random. Only in retrospect, by correlating the two, does the underlying order appear. This kind of behavior challenges our deepest intuitions. In classical physics, an event has a cause, which produces an effect, and this sequence is unbreakable. The future depends on the past, but never the other way around. But quantum mechanics suggests a more subtle reality. It implies that what we think of as cause and effect may be entangled across time, not just space. That what will happen can help define what has happened, that the boundary between the observer and the observed, and between past and future, is less rigid than we once thought. Some interpretations of quantum mechanics attempt to explain this paradox. The Copenhagen interpretation would say that the quantum system remains undefined until observed, and that the measurement, even if delayed, completes the system. The many worlds interpretation avoids collapse altogether and suggests that all outcomes occur and that the observer's experience simply splits along with the universe. In that view, the delayed choice merely determines which branch the observer finds themselves in. But none of these interpretations fully resolve the strange feeling of retroactivity. They only offer different ways to live with the uncertainty. Others invoke the idea of non-locality, the notion that in the quantum world, events are not confined to a single point in space or time. Entangled particles do not obey classical separations. They exist in a joint state that defies conventional geometry. So perhaps it is not that the future changes the past, but that the entire experimental system exists as a whole. In such a framework, asking when the particle decides how to behave might be the wrong question. There is no single moment, only a web of relations, forming a tapestry of probability and outcome. Yet, despite all these explanations, the emotional weight of the delayed choice quantum eraser remains. It whispers to us that reality is not a static film strip, playing from beginning to end. It is more like an evolving narrative, responsive, interactive, and co-created between matter, measurement, and mind. It asks us to consider that the universe is not simply observed, that our measurements, our curiosity, our questions shape the reality we experience, even across time. Philosophically, this challenges our notions of destiny, freedom, and the nature of knowledge. If outcomes are not fixed until measurement, what does that say about determinism? If reality waits for our choices, how far does that waiting extend? Does the moon exist when we're not looking? Does the path of a particle depend on how we will think about it in the future? Are we part of a universe that listens? In the end, the delayed choice quantum eraser does not give us simple answers. It invites us into mystery. It reminds us that science, at its most profound, is not about certainty, but about humility. About approaching the world with wonder, knowing that even our most precise instruments and elegant theories may only scratch the surface of what is. It shows us that time, once thought to be a river flowing in one direction, may be more like a sea, fluid, interactive, alive with patterns we are only beginning to see. So when we gaze at the stars or peer into the heart of an atom, we do so not just as observers, but as participants. Our presence matters, our choices matter, and perhaps, in ways we cannot yet comprehend, they echo not only into the future, but into the very fabric of the past. Quantum Entanglement Paradox. In the quiet depths of quantum physics, there exists a phenomenon so mysterious and counterintuitive that even Einstein himself called it spooky action at a distance. It is known as quantum entanglement, a bizarre link between particles that persists regardless of how far apart they are. When two particles become entangled, they are no longer separate entities. They become part of a single unified system where the state of one instantly influences the state of the other, even if they are light years apart. This isn't just speculation or a strange metaphor. It's a well-tested and repeatedly confirmed feature of the quantum world. And yet, it defies the very fabric of our classical understanding of space, time, and causality. At the center of this deep puzzle lies the EPR paradox, a thought experiment that dared to challenge the completeness of quantum mechanics. The story begins in 1935 with a paper written by three of the most prominent thinkers in physics: Albert Einstein, Boris Podolsky, and Nathan Rosen. Their aim was simple but bold: to expose what they believed was a fundamental flaw in quantum theory. They did not deny the mathematical success of the theory, nor its predictive power, but they questioned its philosophical implication. The quantum world, according to prevailing interpretations, was inherently uncertain. A particle didn't have a definite position or momentum until it was measured. Until then, it existed as a wave of probabilities. Einstein and his colleagues found this deeply unsettling. They believed in a deterministic universe, where objects had definite properties regardless of whether they were being observed. The EPR paper outlined a thought experiment that illustrated this tension. Suppose two particles are created in such a way that their properties are linked. For example, their spins are opposite. If one particle is measured to have spin up, the other must have spin down, and vice versa. According to quantum mechanics, until a measurement is made, each particle exists in a superposition, a blend of all possible spin states. But the moment one particle is measured, the other's state is instantly known, even if it's far away. To Einstein, this implied one of two things. Either information was traveling faster than the speed of light, violating special relativity, or the particles had hidden variables, unknown deterministic properties, that explained the outcome in advance. Either way, he concluded that quantum mechanics was incomplete. This is the essence of the EPR paradox. It asks, how can one particle know the state of another instantaneously without any signal traveling between them? Does the act of measurement on one particle truly create the state of the other, no matter the distance? Or is there some deeper level of reality, hidden from us, where these properties are already set, waiting to be revealed? The EPR argument didn't disprove quantum mechanics, but it cast doubt on its completeness. It left the door open for a more intuitive, perhaps even classical, explanation. For decades, the debate raged on, largely in philosophical terms. Then, in 1964, physicist John Bell changed the game. He derived a mathematical inequality, now known as Bell's theorem, that could test whether hidden variables really existed. If the world behaved according to Einstein's vision, the results of measurements on entangled particles should obey certain statistical limits. But if quantum mechanics was correct in its most radical form, those limits could be violated. Bell gave physicists a tool not just to theorize, but to measure the truth. And measure they did. Over the following decades, increasingly precise experiments were performed, most notably by Alain Aspect and his team in the 1980s, and more recently with advanced photon detectors and satellite-based systems. The results were astonishing and consistent. Bell's inequalities were violated. Again and again, nature sided with quantum mechanics. Entangled particles behaved in ways that could not be explained by any local hidden variable theory. When one particle was measured, the other responded instantly, as if the space between them did not exist. This confirmation of entanglement is not just a strange footnote in physics. It represents a fundamental shift in our understanding of reality. Entangled particles are not connected by a signal or a wire. They are not sending messages faster than light. Instead, they seem to share a connection that transcends space itself. When one is touched, the other feels it, not through any physical medium, but because they are part of the same whole. In this view, the universe is not made of separate parts interacting across a void, but of deeply interconnected systems, where the whole defines the parts. Still, many questions remain. Does entanglement mean that space is an illusion? That separateness is only a feature of perception, not of physics? Some interpretations, like the Copenhagen view, suggest that reality remains undefined until it is observed, and that the entanglement simply reflects our lack of knowledge until the measurement. Others, like the many worlds interpretation, propose that all outcomes occur, and that entangled particles merely follow correlated paths through an ever-branching multiverse. Then there is the possibility that our very notion of locality, the idea that things must be influenced by their immediate surroundings, is incomplete. Perhaps the universe operates on a deeper level, where space and time are not the ultimate backdrop, but emergent properties rising from a more fundamental, non-local reality. Entanglement in this picture is not a bug in the system, it is a feature, a glimpse into the machinery beneath the observable world. Practically speaking, quantum entanglement has moved from philosophical oddity to technological marvel. It forms the foundation of quantum computing, quantum encryption, and quantum teleportation. Entangled particles can be used to transmit information in ways that are theoretically secure and fundamentally different from anything classical systems can offer. Researchers are building quantum networks, where entangled photons link distant nodes, enabling communication with unprecedented levels of security and coherence. What was once a thought experiment is now the blueprint for the future of information. And yet, for all its utility, the mystery remains. What does it mean that two particles can share a state, even across vast distances? What does it say about consciousness, about observation, about the role of the mind in collapsing possibilities into outcomes? While entanglement does not allow for faster-than-light communication since the outcomes are random and only show correlation in retrospect, it does suggest that our classical picture of isolated local events is incomplete. Philosophers and physicists alike are still grappling with these implications. Some suggest that consciousness itself might be a kind of entangled phenomenon, that minds are not confined to brains but participate in a deeper field of reality. Others argue that the observer is not special, that the universe functions entirely without the need for subjective awareness. But the debate endures, because quantum entanglement challenges us to rethink not only how things are connected, but what it means for things to be at all. Einstein was wrong about entanglement, at least in terms of denying its reality, but his discomfort was not misplaced. The phenomenon forces us to confront a world where distance, causality, and individuality blur into something stranger and more unified. The EPR paradox, once an attempt to expose the limits of quantum theory, has instead become a doorway into its most profound truth. It shows us that the universe is not a collection of separate parts, but a single, deeply interwoven fabric, where the tug on one thread vibrates through the entire structure. In the end, perhaps the true lesson of entanglement is humility, that what we see and touch and measure is only the surface, that beneath the certainty of experience lies a world of potential where particles dance in patterns we cannot fully see but can begin to understand. That even the smallest act of measurement, the gentlest interaction, connects us to something vast, subtle, and profoundly mysterious. So the next time you gaze into the sky or touch the hand of someone you love, remember, you are not separate. You are entangled, not just with another person or another place, but with the entire universe. And in that connection lies not just the mystery of quantum physics, but the enduring wonder of being. Simulation hypothesis paradox. What if everything you know, everything you see, hear, touch, and believe is not real in the way you think it is? What if your memories, your emotions, your sense of self are not the result of organic biology or physical law, but the byproduct of lines of code running inside a cosmic machine? This is the unsettling proposition at the heart of the simulation hypothesis. It is the idea that the universe as we know it might not be the base layer of reality, but rather a sophisticated digital simulation, constructed by an advanced intelligence for purposes unknown. Though it sounds like science fiction, it is a question being seriously debated by philosophers, physicists, and computer scientists alike. And at its core lies a paradox that pierces through the surface of reality and drills into the nature of existence itself. The simulation hypothesis entered mainstream discourse largely through the work of philosopher Nick Bostrom. In 2003, he published a paper proposing that one of the following three statements must be true. Either all advanced civilizations go extinct before developing the ability to run ancestor simulations, or, if they do reach that level, none are interested in simulating their past, or, we are almost certainly living in a simulation. Bostrom's argument wasn't about science fiction, it was about probability. If it's possible to simulate conscious beings, and if civilizations can run trillions of simulations, then statistically, it is far more likely that we are in one of the simulations rather than the original, base reality. At first glance, the logic is disturbingly persuasive. Humanity itself is rapidly approaching the threshold of creating virtual environments that are indistinguishable from reality, at least on sensory levels. Video games are more immersive than ever. Virtual reality systems are advancing. Artificial intelligence is growing more sophisticated. Given enough time, it seems inevitable that future civilizations will create entire virtual worlds populated with conscious beings who do not realize they are simulations. And if they do, why wouldn't they run thousands or millions of them? But here's where the paradox begins to stir. If we are simulated, then our understanding of physics is not necessarily a window into reality, it's a set of rules programmed into the simulation. The constants of nature, the laws of thermodynamics, even the speed of light, could be arbitrary parameters, chosen by the creators of the system. What we believe to be fundamental may only be functional. Our most trusted tools of discovery, logic, mathematics, experimentation, might only be valid within the confines of the simulation, and that means we may never be able to detect the simulation from the inside because the very rules we use to test reality could themselves be part of the illusion. This leads to a chilling question. If we are simulated, can we ever know it for certain? The simulation could be designed to conceal itself. Errors, glitches, or inconsistencies might be edited in real time. Attempts to probe its boundaries might be automatically corrected, just as a video game hides rendering errors from the player's view. Like characters in a dream, we might mistake the dream for waking life because all our experiences occur within it. Consciousness, in this view, is not a product of biology, but of code, and yet we feel it. We feel pain, joy, longing, love. We think, we remember, we suffer. If we are simulations, our emotions are either real within a digital frame or carefully mimicked to appear real, even to ourselves. But if the illusion is perfect, does it matter? Here lies the paradox of meaning within the simulation hypothesis. If we are simulated, are we less real? If our memories were implanted, if our world is generated in real time as we look at it, does that diminish the value of our experiences? Or is experience itself the only reality that matters? Does it truly make a difference whether the world is composed of atoms or algorithms? If the love we feel is indistinguishable from the love felt by any biological mind? This is the strange inversion of the simulation argument. It makes reality seem more fragile, and yet, at the same time, it forces us to reconsider what it even means for something to be real. Some take comfort in the possibility. If our world is simulated, perhaps death is not final. Perhaps our consciousness is backed up, or transferable, or restorable. Perhaps the creators of the simulation are watching, or even guiding us. Maybe we're part of an experiment, a narrative, a test. Others find the idea terrifying, that we are not autonomous beings, but artifacts, that our lives are not unfolding freely, but according to someone else's program. The simulation hypothesis plays directly into our deepest existential fears: the loss of agency, the fear of manipulation, the possibility that everything we know is a lie. But it also leads to a unique kind of humility. If the universe is simulated, then the grandiosity of science, the dogma of certainty, the arrogance of explanation, all collapse into something softer, more curious. We become like characters in a book, sentient paragraphs on a page, trying to understand the author not from outside the narrative, but from within it. We wonder whether the simulation has rules we can bend, whether miracles are simply permissions in the code, whether enlightenment is a kind of hack, an awareness that frees us, not physically, but spiritually. And yet, for all its philosophical depth, the simulation hypothesis is limited by one critical flaw. It is unfalsifiable. There may be no experiment that can definitively prove or disprove that we are in a simulation. Even if we detected an inconsistency, it might simply mean we've misunderstood some aspect of physics. And even if we found no inconsistencies, that does not prove the absence of simulation. The system may be too perfect. This makes the simulation hypothesis scientifically impotent. It cannot be tested in the traditional sense. But it remains intellectually potent because it challenges our assumptions about consciousness, reality, and the boundary between the natural and the artificial. Quantum mechanics, curiously, provides some strange parallels. The observer effect, wave function collapse, and quantum entanglement all hint at a universe that behaves as if it is being watched, calculated, rendered. The universe only decides on an outcome when it is observed, much like a computer game that renders a new environment only when the player turns their view toward it. In this way, some physicists have speculated that the nature of quantum randomness might be evidence of computational processes running behind the curtain of our reality. There are also more playful aspects. If the universe is a simulation, then what is the resolution of our reality? What is the frame rate? Is there pixelation at the smallest scales? Are Planck units the universe's smallest bits, the lowest denominator of computation? Are black holes memory limits? Is dark matter a side effect of processor constraints? It's speculative, yes, but also irresistible. The simulation hypothesis makes every aspect of reality feel like a clue, every scientific mystery a potential glimpse into the source code of existence. But perhaps the most sobering implication of the simulation paradox is this. If we are in a simulation, and we reach a point where we can build our own simulations, then those simulated beings may create their own, and so on. A hierarchy of simulated realities, worlds within worlds, stacked like Russian dolls. How many layers deep are we, and what happens if the simulation ends? Do we cease to exist? Or simply become part of another? Is there ever a base layer, or is recursion the fundamental structure of reality itself? Ultimately, the simulation hypothesis doesn't claim that we are in a simulation. It only claims that the possibility cannot be dismissed, and that, perhaps, is its true power. It forces us to confront our assumptions, to ask what we mean by real, to examine whether truth is something that lies outside experience or is embedded within it. It invites humility, wonder, curiosity, and caution. Whether we are carbon-based life forms in a universe of stars, or digital constructs in a universe of code, the question remains, what will we do with our awareness? Because, simulated or not, we feel, we choose, we love, we fear. The beauty of a sunrise, the ache of loss, the joy of connection, these things define us, and whether they arise from neurons or numbers, they are meaningful. The simulation paradox may unsettle the ground beneath our feet, but it also reminds us that meaning is not found in the source of reality, but in how we live within it. Holographic Paradox. What if everything we know, everything we call the universe, from the smallest atom to the largest galaxy, is not quite what it seems? What if the reality we live in is not three-dimensional at its core, but an illusion projected from a deeper, two-dimensional boundary we can't directly see? This is not metaphor, not the stuff of science fiction. This is the holographic paradox, one of the most intriguing and confounding ideas in modern theoretical physics. It suggests that all of the information contained within our three-dimensional universe may actually be stored on a two-dimensional surface at its outer edges, like a cosmic hologram. And if this is true, then reality as we experience it is far more mysterious and far less solid than we ever imagined. The roots of the holographic paradox lie in the strange, intense physics of black holes. These dense, mysterious objects are places where gravity becomes so strong that nothing, not even light, can escape. At the heart of a black hole lies the singularity, a point of infinite density and vanishing volume. Around it is the event horizon, the point of no return. For decades, physicists studied black holes as exotic, theoretical objects that could teach us about gravity, time, and the structure of space itself. But one problem persisted. What happens to information when it falls into a black hole? According to classical physics, information is never lost. Even if you burn a book, the information it contains is not destroyed, it's simply rearranged in the smoke, ash, and heat. But black holes seem to violate this rule. When something falls into a black hole, it appears to vanish entirely. If the black hole eventually evaporates through Hawking radiation, as Stephen Hawking proposed, the matter inside is gone, and with it the information it carried. This creates a paradox. The laws of quantum mechanics insist that information must be preserved, but black holes seem to erase it. This conflict between quantum theory and general relativity became one of the great puzzles of modern physics, but it also opened the door to a radical idea. Maybe the information that falls into a black hole isn't destroyed, maybe it's somehow preserved, not within the black hole's volume but on its surface. This notion was first proposed by physicist Gerard T. Hooft and Leonard Susskind, who suggested that the information contained within a black hole could be encoded on its event horizon. That idea became the foundation for what we now call the holographic principle. The holographic principle posits that the entire universe works like this, not just black holes. That all the data, all the physics, all the particles and fields we see around us are like a three-dimensional projection of a two-dimensional source. Just as a hologram can appear three-dimensional while being stored on a flat surface, our universe might be a projection of quantum information encoded at the boundary of space. This doesn't mean our experience is fake, or that we live in a literal illusion. It means that the fundamental description of our world may be simpler than it appears, and that space itself may not be as continuous and local as we once believed. This idea was given powerful mathematical support through string theory and, more specifically, the ADETS/CFT correspondence discovered by Juan Maldacena in the late 1990s. In this framework, a universe with gravity inside a certain kind of space, a negatively curved anti-de Sitter space, can be fully described by a quantum field theory that lives on its boundary, a space without gravity. Two different theories, one with gravity and one without, describe the same reality. This duality stunned physicists because it suggested that gravity and space-time itself could emerge from a more fundamental, non-gravitational theory on a lower dimensional surface. Although our universe is not shaped like an anti-de Sitter space, the principle may still apply. If true, it would mean that space and gravity are not fundamental at all, but emergent. That what we perceive as distance and location arises from entanglement patterns in a deeper, more abstract layer of physics. The upshot is profound. The universe is not a collection of things in space, but an emergent pattern of information. Matter and energy, time and motion, all arise from this encoded structure. The world is real, but its deepest reality is not in the space we see, but in the boundary we cannot touch. The paradox, then, is one of perception. We live in what feels like a solid, continuous world. We move through space. We watch planets orbit and stars collapse. But if the holographic principle is correct, all of this is the unfolding of a deeper informational reality, one that may not contain space as we know it at all. The paradox is not that we are wrong to experience space, but that space may not be fundamental. The fabric of the universe is not woven from distances and directions, but from relationships and correlations in quantum information. This shift in understanding parallels a deepening philosophical insight. For thousands of years, humans believed the Earth was the center of the universe. Then we discovered that Earth orbits the Sun, and the Sun is just one star among billions. Then we discovered that even the stars we see are just a tiny fraction of what exists. Now, we face a new kind of decentering, not of our location, but of our intuition. We may not be living in a universe of things, but in a universe of information, and our very concept of real may have to be rewritten. But how would we know? Can we ever test whether our reality is holographic? Scientists are trying. Experiments are being designed to detect signs that space is not truly continuous, but pixelated at the smallest scales, like the digital resolution of a screen. If there is a finite amount of information per unit of area, as the holographic principle suggests, then perhaps this will show up in subtle noise patterns in gravitational wave detectors or in cosmic radiation. So far, no definitive evidence has emerged, but the pursuit continues, driven not by certainty, but by curiosity. And even if we never detect the boundary directly, the idea has already reshaped physics. It has provided insights into black holes, entropy, quantum gravity, and the nature of spacetime itself. It has inspired new models of cosmology, new views of the early universe, and new ways to think about entanglement and emergence. It offers a bridge between the quantum and the cosmic, between the bits of information and the geometry of space. But perhaps its most profound impact is philosophical. If the universe is holographic, then what we perceive is not the whole story. There is something deeper, hidden not by distance, but by abstraction. The paradox is that in searching outward into stars and galaxies, we may be looking away from the true foundation. Reality may not lie in the vastness of space, but in the invisible web of relationships that hold everything together. The paradox is that the farther we look, the more we are called inward, not into ourselves, but into the fabric of meaning itself. And yet, for all its abstraction, the holographic principle does not diminish the beauty of the world. A sunset still stirs the heart, a whispered truth still changes lives, a newborn's cry still echoes with the weight of eternity. Whether projected or not, these experiences matter, because meaning is not destroyed by abstraction, it is deepened. If the universe is a hologram, then it is a luminous one, rich with wonder and layered with mystery. A cosmos where the illusion of space is not a deception, but a door, an invitation to think, to question, and to imagine what lies just beyond the edge of perception. In the end, the holographic paradox does not tell us what reality is. It asks us to reconsider what we think it must be. It invites us to let go of certainty, to hold space for the possibility that the world is not what it seems, not because it is false, but because it is more connected, more subtle, more surprising, a universe where surface and depth are one and the same, a universe that, like a hologram, reveals more the deeper you look. Maxwell's demon. In the deep stillness of the 19th century scientific world, a peculiar thought experiment emerged, one that would echo far beyond the realms of classical physics. It wasn't a machine, or a formula, or a laboratory breakthrough, but a demon. Not a demon of myth or religion, but a theoretical being, born of the mind of James Clerk Maxwell. Maxwell, already one of the towering figures of physics, who unified electricity and magnetism into a single elegant theory, now turned to the second law of thermodynamics, the principle that dictates the irreversibility of processes, the arrow of time, the gradual and inevitable increase of disorder. And into this stable law, this seemingly untouchable truth, he introduced a tiny, mischievous paradox. Maxwell's demon. The setup is simple but devilishly clever. Imagine a container of gas, divided into two chambers by a wall with a tiny door. The gas is initially in thermal equilibrium, its molecules bouncing randomly around with equal energy in both chambers. Now, imagine a microscopic demon capable of seeing every individual molecule. The demon opens the door selectively, allowing only fast-moving molecules to pass into the right chamber, and only slow-moving ones into the left. Over time, the right side heats up and the left side cools down. A temperature gradient emerges where there once was none. Without adding energy, without doing any apparent work, the demon has decreased entropy, violated the second law of thermodynamics. It has, in essence, created order from chaos. This is the paradox. The second law of thermodynamics is a cornerstone of physical reality. It tells us that entropy, the measure of disorder, tends to increase over time in a closed system. This is why hot coffee cools, why buildings crumble, why time only flows in one direction. The law is not about specific motions, but about statistics, about likelihoods, about the fact that there are far more ways for systems to be disordered than ordered. The universe, left to itself, tends toward greater entropy. But here, Maxwell's demon seems to push against that tide. It acts as a gatekeeper, a sorter, an arbiter of energy, and, in doing so, it seems to reverse the fundamental thermodynamic flow. At first, Maxwell's demon was merely a curiosity, a way to probe the limits of thermodynamic laws, but as the years passed, the thought experiment grew more significant. It became a battleground for debates not just about energy, but about information. For the demon to perform its task, it must observe, it must measure the velocity of molecules and record that information. This leads to a new insight. Perhaps the cost of defeating the second law is hidden, not in energy, but in knowledge. Perhaps the demon cannot violate thermodynamics unless it also violates the rules of information theory. This idea was taken up in the 20th century by physicists such as Leo Szilard, who connected Maxwell's demon to the emerging field of information science. Szilard showed that measurement itself does not necessarily cost energy, but erasing information does. When the demon resets its memory, preparing to sort the next molecule, it must clear its mental register, and according to Landauer's principle, this act of erasure is not free. It releases heat. It increases entropy. The demon, in resetting its mind, pays the thermodynamic price. Thus, the second law is upheld, not through the motion of molecules, but through the logic of information. The paradox is resolved, not by denying the demon's existence, but by recognizing the hidden costs of knowledge. This resolution is elegant, but it opens the door to something deeper. It suggests that information is not just abstract, it is physical. To store, erase, or manipulate data is to interact with the thermodynamic fabric of the universe. Information has entropy, computation has cost. The mind, like the machine, obeys the laws of physics. This is not just a technical insight, it is a philosophical one. It bridges the gap between thought and matter, between logic and heat. It tells us that knowing is doing, that observation leaves a footprint in the real. And yet Maxwell's demon continues to haunt physics. It remains a metaphor for the limits of control, for the dream of perfect knowledge, for the temptation to cheat nature's rules. In the age of quantum mechanics, the demon takes on new faces. Quantum demons, like their classical cousin, attempt to sort particles and extract work, but now they must contend not only with the rules of thermodynamics, but with the strange uncertainties of the quantum world, where observation collapses states, where entanglement connects distant particles, where information cannot be copied without consequence. In this realm, the demon becomes a shadow of the measurement problem, a reflection of the mysterious link between observer and system. Quantum versions of Maxwell's demon have been constructed in laboratories, using feedback control and measurement to extract work from noise. These experiments do not violate thermodynamics, but they push its boundaries. They show that information is fuel, that knowledge, carefully applied, can be transformed into useful energy. In this sense, Maxwell's demon has become a symbol not of defiance, but of innovation. It shows us that the universe is not a closed, cold machine, but a system where knowledge itself is a kind of power. But perhaps the most lasting power of the demon is not in its scientific consequences, but in its philosophical challenge. It invites us to ask, what is the cost of order? What must be spent to reduce uncertainty? It reminds us that every act of selection, every choice, every thought carries an invisible weight. In a world governed by entropy, order is precious, and wherever it appears, someone or something must pay for it. Maxwell's demon also resonates with our own internal experience. Like the demon, our minds sort chaos into meaning. We filter sensory noise into coherent perception. We prioritize, we focus, we decide. In a world of entropy, we impose structure, not always accurately, not always efficiently, but always with cost. The act of consciousness, of awareness, is a kind of sorting, and like the demon, we cannot do it for free. It drains energy, it generates heat, it wears us down. But it is also the source of life, of mind, of meaning. In modern times, Maxwell's demon has taken on new symbolic dimensions. In artificial intelligence, in computational neuroscience, in theories of the brain as a prediction machine, the demon reappears. Our neural circuits, always on the edge of chaos, are shaped by past experience and future expectation. They compress information, discard noise, and minimize surprise. In this way, every human brain contains a little demon, one that tries, with limited resources, to carve order from entropy. And yet, for all its cleverness, the demon cannot escape the laws it tries to defy. There is no free lunch in physics, no costless computation, no thought without thermodynamic consequence. This is the final resolution of the paradox, not a denial of its logic, but an expansion of our understanding. Maxwell's demon does not break the rules, it reveals them. It teaches us that energy and information are two sides of the same coin, that to know something is to touch it, change it, warm it. So we are left with a strange but beautiful truth. The second law of thermodynamics, the tendency of systems to move toward disorder, is not a barrier to knowledge. It is the stage on which knowledge must act. Entropy is not the enemy, it is the canvas. And Maxwell's demon, once imagined as a mischievous saboteur, now stands as a guide, a reminder that every bit of clarity, every flash of insight, every moment of awareness has its price. In the end, the demon's power is not in what it breaks, but in what it reveals. That the universe, in all its apparent indifference, still responds to thought. That the boundaries between mind and matter, energy and information, chaos and order, are not fixed, but fluid. That behind every door we open, there is another, waiting. And behind that, perhaps, another demon, watching, and, always, paying the price of knowing. Olbers Paradox. Why is the night sky dark? At first glance, the question seems too simple to be meaningful. Of course the night is dark, because the sun has set. But as soon as we look beyond the earth and into the vast cosmos that surrounds it, the question becomes deeper and stranger. If the universe is filled with stars, scattered evenly across infinite space, and if the light from those stars travels endlessly through the void, then the sky should not be dark at all. It should be blazing with starlight in every direction. Every point in the sky should be the surface of a distant star. The night should be bright, yet it isn't. It is overwhelmingly black, speckled only by stars that shine like whispers in an endless silence. This contradiction between expectation and observation is known as Olbers Paradox. Named after the German astronomer Heinrich Wilhelm Olbers, who wrote about it in 1823, the paradox is actually far older. Versions of the same question can be found in the writings of Kepler, and even earlier, but Olbers gave it enduring form. He asked, if the universe is infinite, uniform and eternal, then why is the night sky not ablaze with light? If you look in any direction in such a universe, your line of sight should eventually land on a star. Much like a dense forest, where every direction reveals a tree trunk, an infinite universe should reveal a star in every patch of sky. The entire sky should be bright as the surface of the sun, This reasoning is compelling and deeply disturbing. It suggests that something about our assumptions is wrong. Either the universe is not infinite, or it is not eternal, or it is not uniformly filled with stars, or perhaps something else is preventing the light from reaching us. Some early thinkers proposed that clouds of cosmic dust might block the starlight. But this doesn't solve the problem. Over time, the dust would absorb energy, heat up, and radiate light itself. Eventually, it too would glow, and the sky would still be bright. Darkness persists. The dust cannot be the answer. The resolution of Olbers Paradox requires a deeper understanding of cosmology, of time, light, and the very shape of the universe. The key insight is that the universe is not static. It is not eternal and unchanging. It is expanding. It had a beginning, and this changes everything. We now know that the universe originated from a hot, dense state roughly 13.8 billion years ago, the moment we call the Big Bang. This means the universe has a finite age, and because light travels at a finite speed, we can only see as far as light has had time to travel since that beginning. This defines our observable universe. Anything farther away is still invisible because its light hasn't reached us yet. So, the night sky is dark, in part, because we live in a universe with a horizon, a limit to how far we can see. There simply hasn't been enough time for light from all stars to fill every corner of our sky. The universe is too young for that. But, even more importantly, the universe is expanding. As space stretches, it carries light with it. The wavelengths of distant starlight are stretched too, red-shifted into longer wavelengths, beyond visible light. The most ancient light, from the earliest stars and galaxies, is stretched so much that it becomes infrared or microwave radiation. It is still there, but our eyes cannot see it. In fact, the sky is not completely dark. It glows faintly with the cosmic microwave background radiation, a relic from the early universe, now stretched into cold microwaves by billions of years of expansion. If our eyes could see in that frequency, the sky would shine with a soft, even glow. But to us it appears black, silent, empty. The paradox dissolves, not through a trick, but through a revolution in our understanding of space and time. Olbers' paradox is therefore not a failure of reasoning. It is a gateway, a question that opened a path to deeper truths. It reminds us that the universe we see is not the whole of what exists, that our vision is shaped by time, by distance, by the finite speed of light, and by the restless motion of cosmic expansion. The darkness is not the absence of stars, but the presence of boundaries. Boundaries not in space, but in time. There is also something poetic about the resolution. The night is dark because the universe is young, because not all light has arrived, because we are still in the early morning of cosmic time. It's a reminder that we live in a dynamic, unfinished universe, that creation is ongoing, that the silence we see above us is not emptiness, but distance, a vast unfolding still in progress. Some thinkers have gone further, asking whether the darkness of the night sky is also a condition for life. If the sky were bright with starlight in every direction, if the earth were constantly bathed in the light of infinite suns, would it be possible for life to evolve? Would there be darkness for rest? Would there be seasons, rhythms, contrasts? In this view, the dark sky is not just a mystery, but a necessity, a canvas against which life's drama can unfold. And yet, Olbers' paradox still resonates because it touches something primal. Our ancestors looked up at the night and wondered at its depth. They saw gods, stories, omens. We look up and see galaxies, quasars, the afterglow of the Big Bang. But the awe is the same. The darkness is not just a question of physics, it is a mirror for our curiosity. It challenges us to look deeper, to ask why things are the way they are. And sometimes, the simplest questions open the deepest doors. The paradox also hints at the limitations of human perspective. We are embedded in the fabric of space-time, limited by what light can reach us. Our picture of the cosmos is always partial. There are stars whose light will never touch us, galaxies forever beyond our horizon. The universe may be infinite, but our view is not. And in that gap, the darkness endures. Still, the night sky is not truly empty. Every star we see is a message from the past. Every patch of blackness may contain galaxies too far to be seen, or light too faint to detect. The darkness is not absence, it is depth. A depth that humbles and inspires. It reminds us that knowledge is not just about answers, but about the courage to ask impossible questions. Olbers Paradox did not give us a quick solution, but it changed how we see the universe. In this way, the paradox becomes a metaphor for every mystery we face, for every contradiction that forces us to rethink our assumptions. It tells us that reality is not always what we expect, but it is always richer than we imagine. That behind the veil of night lies not a flaw in logic, but a universe more dynamic and complex than the mind can grasp at once. So the next time you look up at the stars, consider what you do not see. The light that has not yet arrived, the galaxies hidden by distance and redshift, the past that is still on its way. Remember that the darkness between the stars is not a void, it is a boundary of the knowable, a horizon written in time, not space. A paradox once feared, now understood, and like all great paradoxes, it does not close the book, it opens it. Information Causality Paradox. In the invisible dance between particles and probabilities, one of the strangest principles in quantum mechanics is not about what we can see, but about what we can know. It's not just about where things are, or how they move, but about how information flows between them and whether that flow respects the most fundamental rules of cause and effect. At the heart of this inquiry lies a subtle and fascinating idea called the Information Causality Paradox. It is a modern paradox, born not from the physics of motion, but from the physics of knowledge. And at its core, it asks whether the universe allows too much power, too much insight, to pass between seemingly distant systems. Whether, beneath the surface, nature preserves the balance of information, or lets it unravel into something unrecognizably strange. To understand this paradox, we must first return to the quantum world's most perplexing feature, entanglement. Entangled particles behave as a single system, no matter how far apart they are. Measure one, and the state of the other is instantly known. This doesn't allow faster-than-light communication because the outcomes are random, but it does allow correlations that seem stronger than anything allowed by classical physics. These correlations violate Bell's inequalities, revealing that quantum mechanics permits a kind of coordination between particles that defies classical expectations. This strange feature is already deeply counterintuitive, but it still obeys a higher law. No information can be transmitted faster than light. This is the principle of no signaling. It preserves the cause-effect structure of relativity and keeps the speed limit of the universe intact. But then, researchers began to ask a deeper question. Suppose we accept the no signaling condition. That is, even if two distant observers can share entanglement, they cannot use it to send messages instantaneously. That much is clear. But is this the only limit on how much information they can share? Or does nature impose a stricter rule? In 2009, physicists Marcin Polchinski, Tomasz Peterek, Dagomir Kozłowski, and their colleagues introduced a new principle, one that extended beyond no signaling. They called it information causality, and it proposed a limit not just on communication speed, but on the amount of information one party can gain from another. And that's where the paradox emerges. Imagine a game. Two players, Alice and Bob, are separated by a great distance. Alice is given a long string of bits, random 0s and 1s, and Bob is given a number that points to one of those bits. His task is to correctly guess the value of that particular bit in Alice's string. To help him, Alice is allowed to send Bob just one bit of information. That's the rule. Now, in a classical world, even with the most clever strategies, Bob should not be able to learn more than one bit of Alice's string. The amount of accessible information cannot exceed what was transmitted. This is the essence of information causality. The information gained cannot exceed the information sent. But what if Alice and Bob share quantum entanglement before the game begins? What if they use that entanglement, together with the one-bit message, to outsmart the classical limit? In real quantum mechanics, entanglement improves their odds, but not by much. It doesn't allow Bob to learn more than 1 bit's worth of information. In other words, quantum mechanics respects information causality even while violating classical realism. But then comes the twist. Suppose we go beyond quantum mechanics, not in reality but in theory. What if we imagine hypothetical correlations even stronger than those permitted by quantum mechanics, but still consistent with no signaling? These hypothetical systems are called non-local boxes, or Popescu-Roylich boxes, named after the physicists who proposed them. A PR box is a device that allows 2 distant observers to generate outcomes with maximal correlations, stronger than those allowed by quantum mechanics, yet without enabling faster-than-light communication. It's like superentanglement, a kind of perfect coordination that still respects the speed limit of light. These devices are not known to exist in nature, but they are logically possible under the no-signaling rule, and this is where the information causality paradox arises. Using PR boxes, Alice and Bob could win the guessing game far more effectively than quantum mechanics allows. With only a single bit of communication, Bob could, in theory, learn multiple bits of Alice's string. The information received would exceed the information sent. Information causality would be violated. This violation creates a profound tension. If no signaling alone is not enough to preserve the intuitive structure of reality, then what other principles are at play? Why does nature allow quantum correlations, but not superquantum ones? Why does it stop just short of the PR box? The information causality paradox tells us that no signaling is too permissive. It allows worlds where cause and effect are bent by information gain. But our universe doesn't go there. Our universe seems to draw a line at quantum mechanics. And it draws it not because it must, but because doing otherwise would let information flow too freely, breaking the delicate balance between knowledge and communication. This idea that there are deeper constraints than no signaling has become a new lens for understanding quantum theory. Perhaps quantum mechanics is not just a strange set of rules that happen to work. Perhaps it is the unique framework that respects both non-locality and information causality. Any stronger theory would allow too much power. It would enable outcomes that feel like cheating, like guessing without clues, like knowing what was never told. The paradox suggests that the very structure of quantum theory is shaped not just by what can happen, but by what shouldn't happen. It's worth noting that this paradox doesn't tell us anything is wrong with quantum mechanics. On the contrary, it tells us that quantum theory might be just right, just strong enough to be weird, just weak enough to be consistent. It highlights the fact that quantum mechanics walks a razor-thin line between the impossible and the inevitable. It allows entanglement, superposition, and uncertainty, but it does not allow omniscience. It respects boundaries, subtle, mathematical, invisible boundaries that maintain the integrity of causality. Philosophically, the information causality paradox invites us to think about the nature of information itself. Information is not just data. It's power, it's structure, it's the link between events. The paradox reminds us that there are limits to how much information can be passed, how much can be known, and how knowledge must be earned. It hints that reality itself may be protected, not by walls, but by principles, not by distance, but by causality. And that beneath the dazzling correlations of the quantum world, there is a quiet insistence that information must travel in a way that respects the laws of time and logic. The paradox also connects to deeper questions about the foundations of knowledge. If Bob can know more than Alice tells him, then communication becomes distorted. If outcomes can be predicted without cause, then meaning erodes. If information can appear without effort, then the structure of logic itself begins to break down. In this way, the information causality paradox is not just about physics. It is about epistemology, the study of knowing. It is about the thin line between knowledge and noise, between message and magic. In a world where data is everything, where computation grows faster and information flows endlessly, the paradox reminds us that there are still rules. That even the most advanced system must play fair. That reality, for all its mystery, is bound by principles we are only beginning to glimpse. The information causality paradox is one such glimpse. It doesn't shatter our understanding. It refines it. And so we are left once again with a paradox that does not scream contradiction, but whispers truth. A paradox that challenges us not to break the rules, but to understand why the rules exist. Why information matters. Why knowledge is never free. And why, in a universe filled with wonder, even the most powerful correlations are bound by something deeper, something quieter, than we ever thought to question. Boltzmann Brain Paradox. In the grand silence of deep time, long after the stars have burned out and galaxies have drifted apart into darkness, we are left with a universe governed not by creation, but by entropy. This tendency toward disorder, toward randomness, is a central law of thermodynamics, the second law, which states that in a closed system, entropy only increases. But what happens when you take that law and stretch it to its logical extreme? What happens when you ask not just what is likely, but what is possible, however improbable, in a universe that lasts forever? You arrive at one of the strangest and most disorienting thought experiments in modern cosmology. It is the Boltzmann Brain Paradox. A quiet, almost absurd idea that nonetheless carries profound consequences for how we understand reality, time, memory, and the self. The paradox is named after Ludwig Boltzmann, a 19th century physicist who pioneered the statistical understanding of thermodynamics. Boltzmann sought to explain how the orderly structures we see around us, stars, galaxies, even life, can exist in a universe where disorder is the rule. His answer lay in probability. While the natural state of the universe tends toward entropy, it is still possible, though extremely unlikely, for random fluctuations to create pockets of order. Just as air molecules in a room might randomly cluster in one corner, though it's wildly improbable, so too could the universe produce moments of lower entropy, even if they are rare. Over long enough timescales, with enough matter and enough time, anything that can happen will happen, even fleeting bubbles of coherence in an ocean of chaos. Now, imagine such a fluctuation, one so improbable that it defies common sense, yet so inevitable over eternity that it becomes a certainty. In a vast, featureless cosmos approaching heat death, the occasional fluctuation might produce something that looks, briefly, like a galaxy. Rarer still, it might produce something as complex as a human brain, fully formed for just a moment with the illusion of memories, thoughts, and awareness. This brain would blink into existence, have a single moment of conscious experience, then dissolve back into chaos. It would believe itself to be a person, with a past and a life, even though none of it ever happened. This is the Boltzmann brain. And here's where the paradox arises. If the universe is infinite, or lasts for infinite time, then the number of Boltzmann brains it produces will eventually far exceed the number of ordinary observers, like you and me, who arise from stars and planets and biological evolution. In such a cosmos, Boltzmann brains become the statistical norm. They vastly outnumber brains that form through natural processes, and so the deeply unsettling question arises: what are you? Are you a product of billions of years of cosmic evolution? Or are you a random fluctuation in a dying universe, experiencing a dream of reality that never existed? This is not just a philosophical problem, it is a challenge to cosmology itself. Any theory of the universe that predicts more Boltzmann brains than real observers undermines its own credibility. If we take the theory seriously, then we should believe that we are Boltzmann brains, because that is what is most probable under the model. But we do not experience the world as momentary illusions. We see order, continuity, causality, and consistency. We remember our past. We find the future predictable. We have coherent narratives. All of this seems incompatible with the fleeting, disjointed nature of a Boltzmann brain. And so, any theory that makes such brains the norm must be called into question. The paradox then forces cosmologists to examine the assumptions behind their models. Does the universe last forever? Is it infinite in space or time? How does entropy evolve on cosmological scales? Does consciousness require stability, or can it emerge from randomness? These are not idle speculations. They determine the validity of our most ambitious theories about reality. Inflationary cosmology, the multiverse, and eternal expansion all come under scrutiny in light of the Boltzmann brain problem. If a theory predicts too many brains in a vacuum, then it may be predicting too much. The theory might be self-defeating, because if it were true, we'd have no reason to trust our own experiences. There is a poetic horror to the Boltzmann brain idea. Imagine that you, right now, are one such brain. You've just popped into existence, with a vivid memory of reading books, growing up, falling in love, learning science. You believe you're sitting in a room, listening to a voice. You think there's a planet beneath your feet, but none of it is real. It's just information, a statistical fluke. In the next moment, you will vanish. The universe will forget you. No story, no continuity. Just one flicker of awareness in an eternal void. The idea is not just unsettling, it is destabilizing. It calls into question everything we assume about our own reality. And yet, most physicists believe this cannot be, not because the physics forbids it, but because the consequences are too absurd to accept. If your theory predicts that you're more likely a hallucination than a person, then it's your theory, not your experience, that must be wrong. This leads to a kind of inverse reasoning. We trust that we are not Boltzmann brains, therefore we reject any cosmological model that implies we are. This may seem circular, but it's the only way to preserve a coherent epistemology. If you doubt your own experience, you lose the ability to reason at all. You must take your memories and perceptions as a starting point, or nothing can be known. In this way, the Boltzmann brain paradox is not just about physics, it is about belief, about what counts as evidence, about the foundation of knowledge. It touches on deep questions in philosophy of mind, epistemology, and metaphysics. What is a self? What does it mean to have a past? Can consciousness exist without context? Can memories be trusted if they arise without cause? The paradox does not answer these questions. It throws them into sharp relief, forcing us to see how fragile our assumptions are. Some have proposed resolutions. Perhaps the universe is not eternal. Perhaps it decays or recollapses or undergoes a cosmic reset. Perhaps Boltzmann brains are impossible because the conditions required for consciousness cannot emerge from random particles. Perhaps intelligence and awareness require long-term stability, complex feedback, or a grounding in experience. Others suggest that a deeper theory, still unknown, will resolve the paradox by redefining the nature of entropy, or information, or even time itself. But the paradox persists. Like a shadow at the edge of reason, it reminds us that the universe may be stranger than we can comprehend. That in the vastness of eternity, the line between reality and illusion may blur. That even the act of thinking, of questioning, may be an echo in a cosmic silence. And yet, it is precisely this awareness, this ability to reflect, that gives the paradox its power. Because if we are real, then the very fact that we can contemplate our own nature is a kind of proof, a statement of presence. A declaration that we are not just statistical artifacts, but participants in something coherent. In the end, the Boltzmann brain paradox is a warning, not about brains, but about theories. It tells us that any model of the universe must be consistent not just with mathematics, but with experience. That our understanding of time, entropy, and information must preserve the integrity of observation, that theories must not just predict reality, they must explain why we can trust that we are real. So the next time you wonder if the world is an illusion, if your memories are dreams, if your thoughts are echoes of entropy, remember that the question itself is a sign that something deeper persists. That reality, however strange, is not silent. It speaks through paradox. It challenges us not to believe blindly, but to think clearly, and in that act of thinking, of questioning, we find our place, not as flukes in a cold universe, but as minds capable of facing the darkness and choosing to see.